Hello, everyone. Welcome to the February 2025 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. This month's AMA is going to be mercifully short on politics. We're mostly talking about science and other fun things. But, politics still goes on, and we're aware of it. And I'm a big believer that you kind of have to be aware of it and respond to it and think about it and take it seriously while also living the rest of your life. So I'm perfectly happy to be talking about non-political stuff for the AMA, but I do want to note what's going on. I always think about the audience hundreds of years in the future who are wondering what we were thinking back now. And here in February 2025, this is literally a pivotal moment of history. And it would be weird to pretend that it was just a normal moment. We're less than 2 weeks into Donald Trump's second term as president, and it has been even worse of a fiasco than his biggest enemies might have predicted. The combination of ruthlessness and incompetence is quite shocking, and so it's important to remember it, keep it in mind, not act like it's business as usual. One of the biggest things that Trump and his allies have going for them is the idea on the part of everyone else that it's just another political squabble. But it's really not. It's worse than that. Just to remind you very quickly, I can't possibly remember everything, but Trump fired a bunch of inspectors general the moment he got into office. These are government employees whose job it is to make sure there is minimal fraud and corruption. So we're getting rid of them because fraud and corruption are going to be kind of an important catchphrase. He fired a bunch of federal prosecutors, U.S. attorneys, especially ones who had been working on the various felony cases against him at the federal level. He either fired or sent home or convinced to leave a bunch of people at the National Security Council, the director of the Federal Aviation Administration, people at the State Department, people in the Foreign Aid Office. There's a 90-day pause on all foreign assistance. Not all foreign assistance, I shouldn't say that. Israel and Egypt are still getting their assistance, but everywhere else cut off. Ukraine, elsewhere, heartbreaking stories of people trying to, U.S. workers in Africa and elsewhere working to save people in various ways, just having their funds cut off. There was this weird event where there was a memo that went out that said all federal grants are hereby suspended for a while. That would be just enormously destructive to the country. Grants, maybe the word is bad. I don't know. Maybe people don't understand what the word means. It's not like a present. It's money that is used to do important things, like get science done, among other things. So then another memo went out saying, no, the previous memo had been rescinded because they realized how bad it would be. But then the presidential spokesperson, the White House press secretary, said the substance of the memo is still true, even though we rescinded the memo itself. If this doesn't make any sense to you, join the club. It doesn't make any sense to anyone else either. Science has been dramatically affected. This is my own bailiwick. All grant reviews at National Science Foundation, National Institutes of Health, and elsewhere have been suspended indefinitely. I have a grant proposal in, hoping to, fund some research into quantum gravity and cosmology, but that has been put on hold. If it ever comes back, who knows? That's a minor inconvenience for me. The more important thing is that they're not paying salaries to people like postdocs and grad students at the National Science Foundation, for example. For the grad students, I am told it is not such a big deal because if you're a NSF fellow, if you have a fellowship from the National Science Foundation, they allocate your yearly salary in one lump sum at the beginning of the year, and then the university doles it out monthly or whatever. So they should be okay, at least until next year. Postdocs don't have it that good. They have a monthly salary, if they're NSF funded, that is just not coming. They're not getting paid. Postdoc life is not easy, right? You are bouncing around. You have a 3-year job typically at most, and then you have to go somewhere else. You're living paycheck to paycheck, and those paychecks are not coming. So this is going to be catastrophic for them personally. Of course, it's also catastrophic for U.S. science as a whole. Why in the world would the best people from outside the U.S. think of coming here with all of this obvious chaos and dysfunction that we are exhibiting to the rest of the world? Anyway, I could go on for hours about this. I don't want to do that. But there's one other thing I just can't help but mention, because I'm sure that the people of the future are just going to think there's no way that that actually happened. We had fires in Los Angeles not long ago, devastating fires. I used to live in LA, and I know many people who either had to evacuate. Some came very close to losing their houses. Others who are not very close to me but did lose their houses. Many people were significantly, severely affected by these fires. And the response to the fires on the part of the local government was not great. I'm not going to defend it. I think that the California governments, both locally and the state, most of whom are completely run by Democrats, didn't do a great job of preparing for a fire that was quite this bad. You know, some of it is there are unpredictable natural disasters. Some of it is you weren't ready for it, right? So that there's plenty of blame to go around. But Donald Trump somehow got it into his head that it was simply because there was water to fight the fires, and the California government didn't want to turn on the faucet and let the water come down to Los Angeles to be used to fight the fires. This is entirely nonsense. There were times when the water ran out, but it was just because the capacity of the local firefighting infrastructure wasn't up to it because the fires were so bad. There were multiple fires and they were very, very bad. And so firefighters did run out of water, but it wasn't because, as Trump believed, there was plenty of water up in Washington and Oregon and Northern California that could be sent down to Los Angeles, but the Democrats didn't choose to do it. That is entirely wrong. There's no water transport from Washington or Oregon to California. There is plenty of water transport from Northern California down to Los Angeles, but it was working fine. There was no problems with that. But he got it in his head. This is what happens. He's a very not smart person, and he got into his head that all you have to do is turn on the faucet. So he literally ordered the U.S. Army Corps of Engineers to find some dams in Central California and turn on the faucet. So they found two dams in the associated with reservoirs in the Central Valley and opened them, just let them go. Now, they're not going to Los Angeles. These dams are not connected to an aqueduct or a pipeline that brings water. When you open the dams, the reservoirs just empty into the rivers. And this is something that is part of a plan because the Central Valley is the home of an enormous amount of agriculture. And during the summer months, when the drought is usually bad and the crops are most needy, you need that water. You don't need it in January or February in the farmlands of the Central Valley. So this did absolutely nothing. It's literally pouring water into the ocean. And so it was all so that Donald Trump could, on his social media site, put up a little photograph of water pouring out and going, see, I opened the faucet, and if I had been president, these fires in LA never would have happened. Literally what he said. It's inexplicably dumb. That's it's also evil and incompetent, but just the dumbness is what really gets you. So what do we do? I mean, half the country voted for this. Half the country who chose to vote voted for this. We all knew it was going to happen. Like I said, it's been a little bit faster and more dramatic than we expected. But yeah, we live in a democracy, and this is what people wanted. And we have to both live with it and fight against it at the same time. So for the next few hours, we're going to live with it by thinking about other things. The rest of life goes on. The rest of the universe goes on. At other moments, we can resist and think about how to improve the political situation. But meanwhile, we can also think about bigger, more eternal questions. So that's what we're going to do for a little bit. As always, the AMA episodes are brought to you by Patreon supporters of Mindscape. You could become a Patreon supporter by going to patreon.com/Sean M. Carroll and pledging a bit of money for every podcast, or I need to switch it for every month. That's what we're going to be doing now for every month. And as Reward, you get ad-free versions of the podcast. You also get to ask questions. These AMA questions are asked by the Patreon supporters. And every month, every episode, and every regular interview episode, not solos or AMAs, but every regular episode, I do a little reflection audio, talking about how I responded to the interview that we just had, the discussion we just had, and that's for the Patreon supporters. So that could be you if that's how you want to roll. If not, that's also cool. We love you all. Let's go. Cooper starts us off with a priority question. Remember, the priority questions are something that all the Patreon supporters get to ask once in their lives, and I will do my best to answer that one question. We have too many questions to answer all of them. In fact, this month we had a very large number, and I feel very bad. There's a lot of good questions that didn't get chosen, so sorry about that. But Cooper's priority question says, the episode with Jeff Lichtman was fantastic and has really stuck with me. His comment about how understanding something requires compressing it in some way, and how the brain perhaps cannot be compressed in that way, is something I keep thinking about. It's as if the only way to understand a brain is to be a brain. Sort of like how perfectly simulating a universe requires something the size of the universe. Did this comment of Jeff's leave an impression on you as well? Don't feel the need to say much if it did not. No, it did leave an impression, but I've thought about things like that before. I think that there are important differences between levels of understanding. You can understand something a little bit or better, right? It's very similar to the discussion about emergence and higher level macroscopic coarse-grained understandings versus lower level microscopic understandings. So I might not understand everything about a brain, but I understand some things about it. Or think about something that is a little bit less problematic to get all the nuances down. I understand how to drive a car. I don't understand everything that is going on in the car, right? That would require a lot more information. But I can still understand enough to be able to drive the car. And I think the same thing is true with brains. We can understand some things about how they work, or we can focus in on some aspects of them. So the complete understanding might involve something at the Laplace's demon level of perfect information at some microscopic level that we might never obtain, but we can get better and better at understanding bits of it and aspects of it, and I think that's perfectly good. Martin Leitner says, I was wondering how photosensitive organic molecules like chlorophyll in plants or the receptors in our eyes are able to react to a range of frequencies. I was taught that an electron needs a very specific frequency to get excited. Similarly, how can two electrons and two atoms that are not perfectly stationary ever exchange photons given that the Doppler effect will alter the frequency? Well, there's a lot going on here, and I'm actually not the best person to ask about what is going on in the receptors in our eyes or things like that. But I think part of it is there are many different frequencies. So indeed, in the cartoon model of an atom or a molecule, there are electrons in orbitals with very, very specific energies. So you might think that unless you hit that energy right on, you're not going to be able to excite that particular electron. But typically, the photons that are moving around doing the exciting are not in what we call energy eigenstates. That is to say, they don't have perfectly precise, well-defined energies. That's part of the fun of quantum mechanics. In exactly the same way that an electron itself, which if we imagine that it is exactly in a perfectly definite state of energy, it will then not be in a perfectly definite state of position. We think of the electron as being in a superposition of many different positions. These photons are typically going to be in superpositions of many different energies. So the energy has to be pretty close to the right answer to poke the electron around in the right way, but there's probably some uncertainty around that exact right answer, and as long as the electron's energy is within that uncertainty band, you have a probability of making this happen. Remember, all of quantum mechanics is about probabilities for these things happening. And likewise, Yes, the electrons are going to be moving back and forth. They're going to have Doppler effects in the photons that they emit and absorb, but that's sort of helping them, right? In the sense that if you have many different molecules and molecular energy levels are generally tightly compressed. There's a lot of them, so it's not just like the one or two that you see in the cartoon of the hydrogen atom and so forth. So if you have the molecules moving or the photons moving, so there's not only some uncertainty in energy, but some shift in energy because of the Doppler effect, it is more likely that some of the photons are going to be in the right band to do the action. I suspect that, and I don't know this for sure, so you should talk to a real biologist, but I suspect that in the eye, when there is an electrochemical receptor that fires, the probability of that happening per photon, I suspect, is pretty small. I don't know that, but we have a lot of photons in the world. I think that there is some controversy. Now that I'm thinking about it, there's some uncertainty about, is the eye sensitive enough to detect a single photon? And maybe the answer is sometimes it is, sometimes it isn't, depending on what's going on. But anyway, I think that the basic lesson here is there's a lot of uncertainty in quantum mechanics, and this is an example where that actually helps us out. Cole Justo says, in the big picture, you emphasize that emergent phenomena are still real, even if they're not fundamental. How do you differentiate important ontological disagreements from semantics? In what way do you think real has a definite meaning that is worth arguing for? Whether it's worth arguing for or not, I think that's a bit of a judgment call, right? And very often, arguments about whether or not something is real aren't worth arguing for. I don't want to argue about it, honestly. I just want to be clear about what I mean. So if someone wants to say the tables and chairs are not real, I'm not going to expend my precious time here on this earth convincing them that they're wrong. I'm just going to say, look, what I mean by real is it plays some causal role in the universe. It helps me understand what will happen. As I've given the example many times before, if someone says there is a table in the room over here and there are chairs around that table, then instantly certain things appear in my mind, like, oh, so we could go sit at the chairs around the table. We could put our beverages onto the table and it would hold them up, right? So that information that is useful about dealing with the world, predicting what will happen, anticipating what comes next, strategizing between different alternative things, actions we could take and things like that, that's what I mean by real, right? If someone lied, if there were no table in there, or if the table were an illusion, if it were a hologram, then it would not be real because I would mistake what the implications are of that statement. So I don't think it's that controversial or hard. Of course, around the edges, making things perfectly definite can be tricky, but I just try to be clear about what I mean when I use those words. Miran Mizrahi says, I'm guessing that you and Jennifer are reasonably frequent flyers. Do you have any specific approach you take to packing? Do you have sets of travel gear, or do you just pack the same things you use every day? For example, I have a full toiletries bag just for travel. Any packing routines? Are you a light or heavy packer? I think I'm a medium packer. It is true that we travel a decent amount. We're trying to cut down a little bit for various reasons on the amount of travel we do. It was definitely noticeable after the pandemic that we'd gotten out of practice traveling. I do, in fact, have a travel kit with the toiletries and things like that. And, I have a tiny little checklist, like you need the travel kit, you need your phone, you need your computer, you need chargers, right? You need all the different cables that we carry around everywhere we go, passport and things like that. Otherwise, I don't have much of a routine. I try to travel light, but, if you're gonna like go to the gym while you're there, but also go to a fancy dinner and also just be casually walking around the city, then there's already 3 pairs of shoes you need in some sense. So it can be hard sometimes. I don't have any special clues or tips or anything like that. I'm not an expert traveler. I'm not one of these people who dwells in great detail on the most efficient way to pack. For that, you got to go somewhere else. Sorry about that. Scott Collins says, could Laplace's demon predict a Boltzmann brain? Put another way, are random quantum fluctuations theoretically predictable? Well, this comes down to the question of whether or not the ultimate laws of physics are in fact deterministic or not. Laplace's demon is a thought experiment meant to illustrate the implications of determinism in classical physics. That's the whole point. The point of Laplace's demon is that the information needed to predict what comes in the future is implicitly present in the moment right now if you had the complete 100% comprehensive state of the universe. You never do, so that's just a thought experiment, just to try to teach you what determinism really means. In quantum mechanics, for all intents and purposes, in the observable universe, the laws of physics are not deterministic, okay? And I need to put all those words in there with emphases about the observable universe for all intents and purposes, et cetera, because maybe there is a deterministic theory underlying what's going on. Both Bohmian mechanics or pilot wave theories and also many worlds in two very different ways are ultimately deterministic theories. But in both of them, it is impossible for an actual observer in the actual universe to predict what is going to happen next. So it might depend on exactly what kind of what kind of Laplace's demon you have in mind. Laplace's demon in Everett could predict the wave function of the entire universe, but there will be different observers observing different things. That's going to be inevitable, and those observers themselves will never be able to predict what will happen. In a hidden variable model, if that were plausible and fit the data, then presumably Laplace's demon would know what exactly was going to happen. So it depends on what you mean by quantum fluctuations and what you mean by Laplace's demon. Steve Bonner says, priority question. I've always wondered why cosmologists say we need to explain why the baryons in the current universe are almost all matter. If there were nearly equal parts matter and antimatter in the early universe, but randomly just a tad more matter, then after annihilation, that small amount is what you would see today. It looks to us like a lot, but we have no idea how much total matter and antimatter there was to start with. Given any amount of observed residual matter or antimatter, couldn't we come up with an initial combined mass sufficiently large to explain it all as just a small, statistically insignificant imbalance? Well, hopefully you'll not be surprised to learn that cosmologists have thought about this quite a bit. And you have to be careful. Of course, generally, well, let's say one thing. In fact, what cosmologists believe is that there was almost exactly an equal amount of matter and antimatter, but not exactly. And you can work out from the equations and from what you observe how much more matter you needed than antimatter in the early universe. And the answer is about 1 extra proton per billion protons. So for every 10 to the 9 protons and antiprotons, there was 10 to the 9 plus 1 protons for every 10 to the 9 antiprotons. But that's not equal, right? So could you explain it just as an initial condition? Sure. I don't think you can explain it just as a fluctuation, because you have to say a fluctuation of what? You would need some theory of the early universe. Sometimes you have a theory of the early universe, like you have theories like inflation. Right? So in inflation, there is a predictive theory for where the baryons and the antibaryons come from. And you can calculate what the fluctuations should be. They're much, much smaller than 1 part in a billion. Okay, 1 part in a billion is actually a huge difference by the scales that we're talking about here, because there are quantum fluctuations, but there really are not quantum fluctuations. It depends on models of physics that we don't yet have complete handles on, okay? So what you want to do is to create some theory of the initial conditions where there's an imbalance there's not an imbalance in the initial condition, but there's dynamically a preference for, decaying into baryons or antibaryons. And you can invent that. Models of leptogenesis and things like that do that kind of thing. It's a little bit tricky because even in the standard model of particle physics, baryon number is not conserved. B minus L, baryon number minus lepton number, is conserved. So if that quantity is exactly 0, it stays 0, but you can still create or destroy individual baryons. And in fact, we also think that gravity does not conserve baryon number at all. And that hurts you for this particular question, because if you started with an imbalance, but at super duper high energies, there was copious violation of baryon number, then you would tend to equilibrate. You would tend to get rid of the excess number of baryons over antibaryons. So, we don't know what the final answer is. We certainly don't know what the initial conditions are, but cosmologists are thinking about all of these things. And The thing is, it's not just like we don't know why there's more matter than antimatter and this makes us sad, right? That's not the motivation. The motivation is this is a clue that the universe is giving us. There's more matter than antimatter. Okay. Does that tell us something about the laws of physics that we don't know? So, it's nice to have those little puzzles out there in the universe for us to think about. Helen Edwards says, I love all the interviews you've been doing in some form or another on life, how to think about agency, multiple scales, computation, information, etc. Where has your intuition got to on whether AI could ever be alive, and how are you conceptualizing information and computation as a common root of synthetic versus organic systems? Well, information and computation, absolutely a central part of the commonality between synthetic and organic systems. I don't think that my main conception has shifted very much vis-a-vis whether AI could ever be alive. Namely, sure, it could be. I'm 100% willing to imagine that it is being. I think that as I know more and more about what it means to be alive, I'm more and more appreciative of the differences between what we are doing these days in the realm of AI and what it would be to create a truly living artificial organism. As I've said many times before, so I'm not going to rehearse now, but real living beings are quasi-stable systems that take in free energy from the environment and use that free energy to survive, to persist, to self-repair. We do metabolism, we eat and we excrete, and we get on with lives, and we're constantly increasing the entropy of the universe. You can't turn us on and off like you can turn on and off a computer in quite the same way. We have built-in instructions from billions of years of natural selection that lead us to want to survive and to eat and things like that. We're much more self-sufficient than the typical AI system would be. None of these are complete obstacles, right? None of these are things that you couldn't build into an artificial system, which is why I think that that's completely possible. It's just not where we're putting most of our effort right now, right? If you want to optimize for a machine that will create human-sounding sentences and paragraphs on topics that you ask it questions about, then there are much easier ways to do that than to build a full-blown artificial living being, and that's exactly what people are doing. Okay, I'm going to group together two questions. One is from Matthew Cushman, who says, a question from my son Aaron in high school. Suppose there were a small toy universe a few meters in diameter. Alternatively, it could be a region of our universe encased in a reflective, impermeable barrier. The only thing in this universe is an apple. Otherwise, it's static. What would the long-term fate of the universe be? Aaron's theory is that it must eventually end up as photons bouncing around at high temperature due to conservation of energy. And Claudio says, imagine a device, let's say a sphere in which the interior is isolated from the rest of the universe in an absolute way. No radiation or matter of any kind can penetrate. It's even isolated from the CMB, the cosmic microwave background. Could such a device, if feasible, be used to study the cosmological constant and questions such as the heat death of the universe? It's always interesting to me when in 1 month, in one particular AMA session, questions that had never come up before but are closely related to each other just pop into existence. So here we have two people asking about tiny little universes, or tiny little compared to the size of the universe, our actual universe, I suppose, tiny little regions of the universe that are isolated from everything else, what happens inside. So for Matthew/Aaron's question, let's just get one thing on the table very quickly, which is the slight unrealisticness of the question. So there's two different versions, if you remember Aaron's question, either a small toy universe a few meters in diameter or a region of our universe encased in reflective impermeable barrier. So aren't really any reflective impermeable barriers, at least not ones that would last literally forever, right? Because they're made of matter. Just like for the previous question about the matter-antimatter asymmetry, there are questions about physics at super early times and super high energies we don't know the answer to. There's also questions about physics at super long times and low energies we don't know the answer to. Both of them involve, among other things, is baryon number conserved, which is a way of saying are protons stable, right? Maybe they are. We think that they're not. Most physicists think that they're not, but we've never seen one decay. We think, among other things, if you just have ordinary matter, there is a possibility, a sort of probability per unit time, that if you waited long enough would always become real, that the ordinary matter collapses into a black hole, right? And then it would just evaporate away. And that's true for your impermeable barrier also. Even if that doesn't happen, the protons in your barrier could decay themselves, and that would be bad. So it's hard to imagine truly impermeable barriers. It's also hard to imagine small toy universes a few meters in diameter for exactly the reason that Einstein was shocked back in 1917 when he started thinking about cosmology. And he realized that in general relativity, universes tend to either expand or contract. You can't keep the universe fixed, in other words. So that's fine. I'm going to roll with the question. I know what you mean. But I just want people to know that in a world with physics as we currently know it, imagining a small universe that just sits there stationary forever is harder than you think. Okay, so we're going to do it anyway, but it's harder than you think. Okay, so there's an apple in our region. What happens to it? Well, again, what happens to the apple depends on laws of physics that we don't know the answer to. The apple, we think, has a probability per unit time of spontaneously collapsing to make a black hole. And then that black hole would gradually radiate via Hawking radiation. Even if that doesn't happen, the protons and neutrons in the black hole probably also have a probability of decaying into other things if baryon number is not conserved. So I think, as far as our best guesses about physics are concerned, that Aaron's theory is mostly correct, because either the protons and neutrons directly decay in the apple, or and part of the decay, like when the proton decays, it will emit a positron, which will annihilate the electrons in the apple, and mostly you'll be ending up with photons. Now, if it does decay into a black hole, and that black hole turns into photons, details are going to start to matter. How small is this region of space that you have invented? Because it's always possible for those photons to recombine to make another black hole, right? Which would then decay again. And in fact, there's going to be some equilibrium distribution where it's mostly photons. The vast majority of things are photons, but there's a probability that a tiny little black hole pops into existence and then radiates away again. Okay. Now, for Claudio's question, it's a little bit different. Claudio is asking whether or not you could do science in this region. Could you study the cosmological constant in questions such as the heat death of the universe in the sealed-off sphere? Well, in principle, yes. In practice, no. Okay. In principle, you know, the cosmological constant, which is equivalent to the energy density of empty space, has an effect on the geometry of space-time here in our solar system. If that's what you're getting at, then the answer is yes, it absolutely does. So, for example, the orbit of Mercury, which famously was a test of general relativity, because general relativity predicts that Mercury's elliptical orbit precesses a little bit more than Newtonian gravity predicts. The cosmological constant adds a contribution to the predicted precession of the orbit of Mercury. But when you plug in the numbers, that extra addition is so incredibly tiny that breathing on Mercury is probably at least as effective, okay? The numbers actually matter here. And with things like the cosmological constant or the heat death of the universe, size matters. The cosmological constant has effects that build up over space and time. So if you have a small region of space, in principle, there's an effect of the cosmological constant, but that's exactly the wrong place to look for a noticeable effect. That's why, in practice, when we try to constrain the cosmological constant, we are generally doing cosmology experiments. Okay, Pete Faulkner says, in your December 2024 AMA, in response to a question about black holes, you mentioned that details like a black hole's size, composition, and the observer's velocity significantly impact the experience of someone falling into a black hole. This seems to contrast with my understanding of the no-hair theorem, which suggests that black holes are fundamentally characterized by just mass, angular momentum, and electric charge. Could you explain how these seemingly conflicting perspectives are reconciled? Sure. It's the difference between falling in and staying outside. It's as simple as that. If I throw a bunch of things into a black hole, then from the perspective of someone outside, the details of what I've thrown in completely disappear. I mean, things that are just visible, like did I throw in a red ball or a blue ball, that literally disappears. It's now behind the black hole. I just don't know. Things like the lumpiness, the spatial configuration would initially distort the shape of the black hole, but the black hole would quickly radiate away any such distortions in the form of gravitational radiation. So the black holes settle down from the perspective of an outside observer. But if you're falling into the black hole, you could still see what I threw in. If I threw in a ball and you don't know whether it's red or blue, but if you fall in fast enough after the ball, you can just catch up to it and look at it. So it's completely consistent. It's just you're asking two different questions from two different points of view. Robo says, I liked your solo episode 295 on emergence. From the start, I was listening for some description that corresponds to my naive idea that the term emergence refers to the way that lower level states and their dynamics interact on a meta level to generate macro relationships, even if those relationships or influences do not arise from the theory of the micro level. An example from recent experience is Albrecht's law. Intelligent people, when assembled into an organization, will tend toward collective stupidity. Does your idea of type 3 or type 2 emergence encompass this kind of concept, or am I off track even thinking of this as emergence? You're not off track thinking of it as emergence. I think that anything which starts with either individuals and goes to groups, or starts with atoms and goes to individuals, these are examples of emergence. If you can describe the group in terms that don't require specific information about all the elements of the group, then you're doing emergence in some way or the other. I don't know whether Albrecht's law is really true or it's just kind of a joke, right? I'm not exactly sure about that. But I don't think it's fancy emergence in the sense that I think it would be completely predictable on the basis of a competent theory of individuals, right? Like, why are the individuals tending towards stupidity? Like, they react to other individuals in certain ways, and you kind of could have predicted it. Maybe you didn't, but you could have. Just like in principle, if I knew everything about atomic physics and chemistry, I could predict liquids and solids and superconductivity and all those things, right? In practice, it might be very hard, but it's absolutely implicit in the underlying theory. So emergence is great because you don't need to know the underlying theory. I can learn about solids and liquids without knowing about atoms. But that doesn't make them incompatible somehow. And in principle, which is a very, very important phrase in this game, I could tell you about solids and liquids just based on the underlying stuff of which they are made. Gray Monroe asks a priority question. What are your thoughts on the relevance of many worlds quantum mechanics to theories on the origin of life? Many worlds suggests rare branch of the wave function where functioning life, let's call it a Boltzmann cell, emerges by chance. These cells could seed their universe with the first replicating organism, bypassing the challenge of explaining the origins of the first complex cell. Should we seriously consider the possibility that we live in such a world? Sure, you're welcome to consider that possibility. I would, as usual, even though I think that many worlds is probably the best theory we have of quantum mechanics, I don't really care about the other worlds. Like, it's just not the reason why I care about it. The reason why I care about many worlds is because it gets the predictions for our world right. And in our world, what you predict are various quantum probabilities in exactly the same way in many worlds as you do anywhere else, that the probability of something happening is proportional to the wave function squared. The thing about intelligent life is we know it exists because we are it by most definitions of intelligence. So it happened. And if you want to say, well, the probability of it happening, there's some bottleneck, maybe the first cell, maybe some other point along the way, the probability was really, 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 really low. Okay, well, but it happened. We're in the part where it happened. So either it happened because there's a single world and we just got lucky, or it happened because there are multiple worlds and there's an anthropic selection and we're going to find ourselves in the world where it could have happened. The difference between those two things makes no difference, as far as I can tell, to theories of the origin of life, etc. Getting lucky versus anthropic selection have all exactly the same empirical content as far as our world is concerned. So I wouldn't point to many worlds as helping that much there. It might help you feel better about the fact that something unlikely happened, because since we need to conditionalize on life existing, we don't need to conditionalize on other things like the mass of the Higgs boson or whatever, but we wouldn't be having this conversation if life didn't exist. So if there are many, many universes, each one of which it's rare to find life, but one of them was bound to do it, that might help you feel better about the fact that we are in that world, okay? So, but I don't think it really helps you in terms of investigating the details about how life came to be. There's still an empirical question. Is it easy or hard? What is the probability? Many worlds doesn't help you answer those questions. Daniel Schirmer says, if the rotation of the sun was slowed down, could that cause the orbit of the Earth to decay? I heard the Earth would get closer to the sun if the sun's rotation slowed down. How much closer would the Earth get to the sun if the sun was spinning half as fast as it currently does? So you hopefully will not be surprised to hear I have no idea how much closer the Earth would get to the sun if the sun was spinning half as fast as it currently does. I'm not even at all sure that it's true that the orbit of the Earth would decay in a noticeably different way if the sun was slowed down. Or I guess what I should say is I'm not sure whether it would decay at all. It does decay because of various effects that are much, much more important than the rotation of the sun, like the orbit of Jupiter is more important than the rotation of the sun for things like this. And the orbit of Jupiter doesn't matter that much. So the only thing I really have to say about this question is any of these effects are going to be really, really, really small. Isaac Newton did pretty darn well in understanding the orbits of planets and things by treating everything like a point particle that wasn't rotating at all. So that must be a pretty good approximation. Craig Stevens says, I learned in college that photons may be absorbed by atoms if they have the right energy and move a valence electron from one energy level to a higher one. Then when the electron moves back down to the lower level, another photon is emitted. Is there a way that photons can be absorbed and not re-emitted, or are they constantly bouncing from one atom to another or moving through empty space forever? I think that the answer is no, there is not such a way, but I mean, of course, it depends on what you're allowing yourself to do. If you put the so here, let me say what I think is true, and then we can decide what you meant by the question. When you have an atom that has an electron, let's just take a hydrogen atom, right? Let's make it very simple. So you have one proton, which is the nucleus, you have one electron, and there are energy levels, okay? And there is a bottom energy level. There's the ground state energy, the minimum energy state of the electron. And as far as ordinary quantum mechanics goes, so we're ignoring baryon number violation, proton decay, all that stuff, right? All that crazy stuff. In ordinary undergraduate quantum mechanics, if you have a hydrogen atom with its electron in the ground state and you ignore the rest of the world, then it will stay there forever, okay? It's a stable state. It's not going to do anything. It just sits there. If you excite it, so you send a photon in and you prod the electron to a higher energy state, the higher energy states are unstable. They just are. You can predict, this is a classic undergraduate homework set, you can predict, based on what that energy is, the probability per unit time of the electron decaying back down to the ground state and emitting a photon. So if you wait arbitrarily long, the probability approaches 1 that electron will go back down to its ground state. If you want to ask why that happens, why is it necessary, why can't the electron just stay there, then there are many possible answers depending on what kind of answer you're looking for. My favorite answer, which is not the one anyone else gives, but it's because entropy increases. Why is that? Well, because you go from a system that has one proton and one electron to a system that has one proton, one electron, and one photon. There are more ways to have that system arranged than just the one proton and the one electron. So emitting more and more photons increases the entropy of the universe in general. So that's likely to happen and unlikely to unhappen. It can unhappen because you can aim a photon, right? It's just the numbers are small enough that you can control what's going on. But in general, the way to think about it is the electron will want to dissipate any extra energy it has to go down to the ground state, and it does that dissipation by emitting photons, either single or more than one photon sometimes. Thomas DeWitt says, in your recent podcast and paper on emergence, you seem to treat non-locality in time versus space differently. For time, you assume locality in all cases, the Markovian assumption, saying it is not an important assumption because, for example, memories could be introduced at a given time step that have information about the past, while the system remains Markovian. But spatial locality was used to separate types of emergence. Couldn't the analogous thing be done for spatial locality, where knowledge about other locations is contained at each location, making the dynamics local? Is there some crucial difference between time and space that I am missing? Yes, there is a very crucial difference between time and space that you are missing. This is subtle. We all know that Einstein came along and said that in some sense, time and space are both part of a single underlying space-time. You want to say that, and you want to appreciate it, and you want to take it on board in your precious belief set. But you also want to understand that there are still differences between time and space. The single biggest difference, I would say, there's a lot of differences, but the single biggest one is, given information about the universe at one moment in time, you can, in principle, in classical mechanics, predict what it will be like at other moments of time, right? That's Laplace's demon that we were just talking about. There is no analogous statement for space, okay? So the table I have right in front of me right now, it has atoms in it. The atoms have a certain density, right? And knowing the density of atoms, the number, the amount of grams per cubic centimeter at one location of the table does not help me predict what the density of matter is like a few centimeters away, because the table might end, right? There's a sharp line where the table is to the left and it's not to the right. There's a discontinuity in the density of matter. But if I think about, so over space, there's just complete difference from place to place. There's no determination from what happens at one point to what happens at the other point. But there is a determination in time. If I say, okay, there's a certain amount of energy density here at one moment of time, what's it going to be like a minute later? It depends on details, but probably it's going to be the same number, right? The table's not really moving. So there is this rigidity, there's this predictability from moment to moment in time that simply isn't there in space. And this has to do with the fact that there is only one dimension of time. This allows for that fact to happen. Mathematically, it has to do with the hyperbolic nature of the underlying differential equations. But there are three dimensions of space, so you don't quite have that same rigid control. So yes, in practice, for the reasons that we care about here, time and space are pretty different. There's predictability in time, not predictability in space. Anonymous says, I've noticed you almost never swear on the podcast. I'm curious if this is in order to be professional, or is that how you are in daily life as well? I think that in daily life, I swear more than I do on the podcast, okay? I'm not afraid of swearing. I'm happy to do it. But yeah, I don't know whether you want to call it professional or not, but I do try to respect the audience and try to care about what the audience is. Some members of the audience would probably like it better if I swore more. Some would not like it better. I'm going to, play it cautious and just try to be, as accommodating for the largest number of people that I can. Okay, so when I give a talk, when I'm giving a colloquium or something like that, there's no swearing going on, right? When I give a public lecture, there might be children in the audience, there might be adults who just don't like it. So there is a certain standard of behavior that one adopts that I'm perfectly happy to do. One can always violate the rules in strategic ways, right? For emphasis, if you want to make a point especially hard, if there's a guest that I'm interviewing and they swear a blue streak, then sometimes that's going to happen. Thi Nguyen was definitely like that, for example. There have been others. I remember when I was an undergraduate and I took a class, a philosophy class actually, and the professor had, he missed the first class. So because he was traveling, he was at a conference and he came back for the second class and he was talking about, he was sort of getting to know us and just sort of schmoozing or whatever before launching into the substance of the course. And he was talking about being in New Orleans, and he ended up in this place in New Orleans, and there was no beer being served. And he was upset about this. He was like, come on, I'm in New Orleans. Where's the fucking beer? And years later, because I got to know him pretty well, he explained that that was entirely pre-planned, that he very intentionally tries to swear in every first class meeting of every class he teaches. Why? Because if he happens to swear, in week 5, it does not seem like such a big deal. He's sort of already set the stage. This is just human relations. This is just accurately gauging what you're trying to do, what the impact of how you talk and what you say is. If you want to get grandiose about it, think about the conversation we had with Derek Guy about how to dress. You can dress however you want, sure. You can talk however you want. You can present yourself however you want. You're totally welcome to do that. It's a free country. But you can't be naive. You can't just say, not only do I want to dress and talk and present myself however I want, but I don't want anyone else to react badly about it, to judge me, to think less or more of me based on how I talk or how I dress or whatever. That you don't have a right to. You can talk and dress however you want, but people are going to react to it one way or another. We all live in a world where there are other people judging us all the time. Maybe you don't care. That's fine. You don't have to care. But if you do care, you should be cognizant of what it is. So I just want the podcast to be as pleasant and enjoyable for as many people as possible. And I talk like I do. I talk in the podcast like I do when I'm being a physics professor, more or less. Soonest Mended says, in the recent solo podcast on time, you argue that the presentism versus eternalism question is important not because one or the other being true would change the predictions of physics, but because believing one or the other might influence future avenues of research in physics. Are there examples of other such questions where choosing a particular orientation has led to a research breakthrough that would otherwise have been unlikely or impossible? I don't know of a perfect example off the top of my head, to be honest. I know exactly what you mean. So there's various places in physics where we have multiple ways of talking about exactly the same processes or phenomena or whatever. A classic example, especially for those of you who have read Volume 1 of The Biggest Ideas in the Universe, Space, Time, and Motion, is the difference between Lagrangian classical mechanics and Hamiltonian classical mechanics. This is to say, for those of you who have not read that wonderful book that I can absolutely recommend to you, you can formulate the laws of physics either in sort of the good old-fashioned Laplace's demon way, which is to say, give me the complete state of the system now, give me the equations of motion, I will tell you what happens next. The Laplacian paradigm, we called it in the book. And that is how Hamiltonian mechanics works. Lagrangian mechanics is based on what's called the principle of least action. You may have heard about it. And it says, don't tell me exactly the state of the system to start. Tell me the configuration of the system. Tell me the positions, but not the velocities, for example, of the system. But then also tell me the configuration of the system at some other time. And I'm going to search through all possible ways to connect the configuration at the early time to the configuration at the late time. I'm going to choose the one that minimizes a certain number called the action, okay? So you can show that the actual behavior of systems under these two ways of talking are completely equivalent, but the actual procedure you go through to get them is very, very different. In a slightly more advanced version of this, these days we talk about the ADS-CFT duality and other dualities in quantum field theory. A duality is exactly this. A duality is two different ways of talking about exactly the same underlying physics, two different equivalent ways of talking. In quantum mechanics, we have the Schrödinger picture and the Heisenberg picture. There's a whole bunch of different examples where you have multiple ways of doing things. I don't know whether there are examples where choosing a particular orientation has led to a research breakthrough. Probably yes, but I don't know off the top of my head. But absolutely it's true that choosing a particular orientation changes how you naturally think about things, right? It changes the sort of natural ways to modify the theory or think about different theories. Anyway, I don't have any perfect examples of that off the top of my head right now, but for presentism versus eternalism, presentists, I should say, I'm an eternalist myself. So I think of the whole shebang, right? I think of, the whole universe all at once and try to figure out what rules it obeys and things like that. Someone like Tim Maudlin, former Mindscape guest, is a presentist. He really thinks that the laws of physics not only describe patterns in the evolution of the universe, but bring them about. He's not only a presentist, but an anti-Humean when it comes to laws of physics, as we talked about with Tim, but also previously with Ned Hall, etc. So Barry Lower and I talked about that also. So that does lead these individuals, myself, Tim Maudlin, etc., to propose different theories of understanding. Tim is not happy with many worlds. He's much happier with Bohmian mechanics. I'm kind of appalled by Bohmian mechanics. Which one of us is right will hopefully be decided by data and things like that in the future. But in the meantime, since we don't know the answer, our orientations are absolutely going to affect what we're most positively predisposed toward. Robert F. asks a priority question. My father always wanted to understand the answer to the question, if mass, a large object, follows the curvature of the fabric of space, wouldn't then there be some kind of small measurable background heat due to friction of its motion through space? So yes and no. Strictly speaking, no. There's not friction due to the motion of objects through space, because the idea that you have that there should be friction comes from a very higher level, non-fundamental description of reality, right? If I push a tire down the road, there is friction because the tire is made of atoms, and the road is made of atoms, and the air through which it moves is made of atoms, and there are photons bouncing off the tire, and in all of these invisible ways, there's noise and friction and dissipation, and energy gets lost from the tire. And so you perceive that as a kind of frictional force that eventually slows down the tire. If I have an elementary particle or a single object moving through the universe, space itself is not made of atoms in the same sense that the tire or the road is made of atoms. There isn't any way for that object to sort of give off energy to the medium around it. The medium around it is as empty as it's possible to be. So strictly speaking, no, there's no friction of that kind because the medium we're talking about is a much more basic element of reality. It's not this collective thing that you get by taking many, many atoms and jiggling them together. Having said all that, there's one kind of tiny caveat, which is that if you move an object back and forth, rather than just like letting it move through space. Actually, sorry, let me back up because I realized I missed a chance to explain something. I can prove that an object moving through space does not slow down. The proof is the following. There's no such thing as a reference frame for velocity in relativity. There's no preferred velocity to the universe. So slow down compared to what? Said in other words, if there was only one object in the universe, I could always describe that object in its rest frame, in the frame in which it's not moving at all. And there it's just not moving. So there's no need for it to give off energy and slow down. And if it just stays there perfectly ordinarily in its rest frame, then in some frame that is moving with respect to it at constant velocity, you will always see it moving at constant velocity. Okay, that's one way of saying it. Which is why if instead I'm shaking it back and forth rather than just having it move at a constant velocity, then it's a different story because then it is coupled to gravity. Everything is coupled to gravity. There's a gravitational field for this massive object that you're shaking back and forth, and there it will emit gravitational waves. It might also emit photons or something like that, electromagnetic waves. But because every object creates gravity, if it's moving on a non-uniform trajectory, it can lose energy by emitting through gravitational waves. Indeed, when you get a detection of gravitational waves at a gravitational wave observatory like LIGO, why do you do it? Well, it's because two black holes were orbiting each other, or a black hole and a neutron star, and they're orbiting, so they're circling around each other. So that's more or less like being shaken back and forth, and they're emitting gravitational waves. And those gravitational waves are what you ultimately observe. The energy loss due to that emission of gravitational waves is what causes the black holes to spiral together and eventually coalesce. There you go. Taylor Gray says, I'm currently reading former Mindscape guest Matt Strassler's book, Waves in an Impossible Sea. The book states that the faster you go past a magnet in the magnetic field, the more you will detect the electric field. What mechanism, for lack of a better term, makes this so? Again, this is a question that the satisfactoriness of the answer is going to depend on your prior exposure to physics. Let me give you the highest level answer right away, which is that according to the theory of relativity, the electric and magnetic fields are just two different aspects of the same underlying field. Exactly in the same way, not exactly, but very, very analogous to how time and space are two different aspects of the same underlying space-time. The electric field and the magnetic field are two different aspects of the underlying electromagnetic field, if you want to put it that way. Very, very roughly, the sort of spatial components are the magnetic field, the temporal, time-like components are the electric field. But that is not exactly right, but it has something to do with it. The point is that when you do a Lorentz transformation, which is to say, if you go from one reference frame, like we were just talking about with a large object, you go from one reference frame to another, which you can do by either moving yourself or by moving the magnet or the charged particle or some other electromagnetic phenomenon. Either you move it or you move you, it doesn't matter. You are now shifting, rotating the different parts of the electromagnetic field into each other, so that exactly for the same reason why moving at a constant velocity means that you define the division of space-time into time and space slightly differently than a person who is not moving in the original reference frame. Now you also define what part of the electromagnetic field is electric and what part of it is magnetic slightly differently. So this was a crucial feature of course, the historical development of relativity. It was first these wonderful experiments done in the mid-1800s that culminated in Maxwell's theory of electromagnetism that showed that empirically you could make an electric field by moving a magnet and vice versa, that eventually led to different transformation laws, Lorentz and Fitzgerald and so forth, and Poincare, and Einstein eventually unifying the whole bit. So the very short answer is the electric magnetic fields are two different aspects of the same single underlying electromagnetic field, and they are transformed into each other by changing your frame of reference. Alex West says, with the general release of AI, have you noticed any fluctuations or trends in both the quality and quantity of peer-reviewed papers and, more personally, emails from the next Einsteins? Well, that's a good question. For peer-reviewed papers, no, I certainly have not. It's a weird thing to me because in my kind of field, the most active people, the people who are most respected in the field basically know each other, and you know what people are doing, and you recognize their names when they write papers, and people write a few papers a year. Some are more prolific than others. But there are these other fields where apparently there exist people who just write, 100 papers a year, which is essentially impossible. It's not the field's fault, because that's not typical in that field, but you can get away with doing that. I can't even read 100 papers a year. But obviously, there's a lot of churn here. People are leaning on other co-authors to do writing, or they're just taking something they've already written and rewriting it 10 different times and submitting it as an extra paper, etc. But that's not my world. In that world, AI might be very, very helpful if all you're trying to do is maximize the number of papers you submit somewhere and publish them in junk journals or whatever. That I don't really follow, so I wouldn't know. In the field that I'm in, I don't think that I've noticed anything at all as a result of AI, except that people are writing papers about AI, which makes perfect sense. As to the next Einstein thing, when I read this question at first, I thought, no, I don't think that there has been an uptick or a change in quality. And I think that there's an explanation for that psychologically. The people who think of the next Einstein, they don't want to hand over credit to an AI, right? They don't want to say, well, the AI and I put this together. They want to say that their own personal genius is responsible for this. But having thought of it and having a few days gone by, it is possible that I'm getting more of those emails. I've always gotten a lot. Arguably, the numbers are small, but it's possible that I'm getting more now. And so maybe they're just not telling me and they are indeed helping themselves to a little bit of AI help when making up their theories of everything. Look, life is short. I don't spend a lot of time paying attention to those papers. So as soon as I can tell that the email is from someone who has a new theory of everything, all they need is for me to fill in the math, that gets filed pretty quickly. Janderson, or some version of letters and numbers, says, in your recent solo episode number 300, you present a way time might be modeled as emerging from the universal wave function. Am I right in assuming that this method could also be used to produce any number of other dimensions of space and time, perhaps? Well, the particular method that I was talking about, the idea, doesn't really work with space. It doesn't really make sense. What you're trying to do is take advantage of the fact that there is two features of quantum mechanics. Number one, entanglement, and number two, superposition. So by entanglement, to get time to emerge, you take advantage of that by saying that there is some clock subsystem that is entangled with the rest of the universe. Okay, and then superposition so that you can take different states corresponding to different configurations at different times and just adding them together in an overall static wave function. But space is just a different kind of thing. Like we said, that evolution through time that is characteristic of the time dimension doesn't happen in the same way in space. So it really is a different kind of thing. Ultimately, probably you want to have everything be unified, but that's tricky to do for a number of reasons. So in the specific approach that I was talking about in that podcast, time is just a very different kind of thing than space. Ben Lloyd asks a priority question. I need your help with something. This might seem weird, but my biggest fear by far is that at some point everything will end forever. I'm not really scared that our civilization will likely not be able to survive the heat death. My main fear is that the universe will end. Nothing interesting will be able to happen anywhere forever, and no multiverse scenarios that would contradict what would turn out to be true. Luckily, many theories or hypotheses make it so that interesting things would happen forever. For example, inflation is the dominant theory for explaining the early universe and how it evolved. And many prominent proponents of inflation often say that eternal inflation is almost inevitable once you get inflation. In eternal inflation, there would be continuously new universes forever. The next biggest competing theories to inflation are cyclic models, etc. I've always needed this sort of existential comfort, but more than that, I need to believe things that have evidence and things that could be true. That's why I'm not religious. Anyway, what do you think of this? Do you align more with my view? I really don't align with your view. I think that I can't let my life here on Earth be vastly affected by things that are going to happen long after the last star stops burning. This is something that I can imagine, but not something that affects my life in any way. I am entirely at peace with the idea that the universe might someday end. Maybe the last living creatures in such a universe will be sad, and that I understand. That makes perfect sense. But we are so enormously far away from that no, it doesn't really affect me very much. And in fact, it's sort of important to not let it affect you too much if you're a scientist or philosopher, because then it will point you towards sort of giving more credence to certain theories than might otherwise be appropriate, even though you don't have a lot of evidence really for them. Funky Town says, for the first 2 decades of my life, I lived in a very small bubble with limited knowledge of the universe's workings and a huge emphasis on religion and the Bible as final truth. For the last decade of my life, I found myself diverging from my original worldview and considering myself a little more enlightened. The biggest struggle for me during this time is trying to understand the feelings and experiences I had in my earlier years and rationalizing them. Is there a physical explanation for the responses someone has that are considered religious experiences, especially if that has been something they have been immersed in during their entire upbringing? For example, I went to a service recently for the first time in years and had a very emotional response despite not putting much stock into the belief anymore. Yeah, I think that I'm not an expert in exactly the neurological or even psychological explanation for these responses, but to me, they seem completely unsurprising. When I walk into a beautiful cathedral or hear really good church music, it is emotionally affecting. Why wouldn't it be? Forget about the existence of God. These things, these cathedrals, these pieces of music were designed by human beings to evoke an emotional response, right? That's why they were designed the way they were. So I have no trouble believing that the physical trappings of a church or the aesthetic trappings of the art or the music, or for that matter, the sort of ritualistic trappings of the steps you go through when you're at a church service have important resonance to us. That is as unsurprising to me as saying, oh, I went to a rock concert and a bunch of people seem to be having a really good time and dancing around. Isn't that surprising? It's not really surprising to me. Robert Granice says, when the universe reaches maximum entropy, heat death, does time end as well? With no more entropy, the arrow of time would cease to have meaning, wouldn't it? Well, as I've said many times before, but it's been a while, so I'll say it again. Time is separate from the arrow of time. Just like space exists without an arrow of space, time can exist without an arrow of time. Time, as we conceptualize it in physics, can absolutely be part of the best description of the universe while not having a directionality one way or the other. So just like there is a distance between me and the sun, even if there are not a bunch of rulers or meter sticks lying between me and the sun to actually measure it, there will be time in the universe once you reach thermal equilibrium. If I have, a glass of water and there's an ice cube in it and the ice cube melts and the water is now more or less in equilibrium at room temperature with the room around it, I can still sensibly talk about how long it's been there. Time is still passing. DI says, how does one stay realistically optimistic within the next 4 years in the United States? Any suggestions for small yet socially meaningful actions each one of us can take? The short answer is not really. I mean, I have suggestions, but I don't necessarily think my suggestions are very good. Different people will respond differently. Different people are going to have different ways of coping. Some people are going to be happy about the next 4 years. But if you're the kind of person who is concerned, worried, anxious about the next 4 years, I do think that it's important to mix trying to do something about it with also trying to live the rest of your life, as I said at the beginning in the intro of the podcast. Doing something about it, means politics one way or the other. It could mean campaigning or something like that, but it also could just mean talking to people. At the end of the day, democracy is not just about putting up more posters. It's about changing people's minds to agree with you. You have to actually communicate with people and give them the sales pitch that your point of view is better. I think that people on both sides of the divide are not very good at that. But if you could, talk to some people who are not closed-minded and not just insult them for not agreeing with you, but actually provide them reasons that it would be better to agree with you, then you've done a little bit to make the country a better place. Meanwhile, take care of yourself. Learn interesting things, listen to good podcasts, keep trying to get better ourselves at understanding the world, both in political ways and in scientific ways. It's an ongoing process. We're not going to declare victory and okay, now the world is good. We're going to try to keep on in little tiny ways, making it better. Sid Huff says, Jan Levin, a former Mindscape guest in a recent episode of Robinson's podcast, stated that astrophysicists don't really care what goes on inside a black hole. The event horizon is the black hole. We simply don't care what's going on inside. Why would she say this? Why wouldn't she and other astrophysicists want to know? Well, astrophysicists are human beings, and a human being might want to know what's going on the inside. What Jana means is that for the purposes of astrophysics, it doesn't matter what's going on inside the black hole. That has to do with the no-hair theorem we were just talking about earlier. Once you throw that stuff into the black hole, and once the black hole settles down, it is entirely defined by what's going on at its event horizon. Astrophysics is not affected by what's going on inside. That's all that she meant. Randall Bessinger says, do you have any views on the current brouhaha in the atheist skeptical movement on the trans issue? I'm not quite sure what kind of views you want me to think about here. I mean, I'm definitely on one side of this issue in the sense that I think that trans people are people and should be treated as such. And it's absolutely true that a certain segment of the atheist skeptic movement has just wandered into really bad territory at being very actively anti-trans in a way that seems very illiberal and immoral, honestly, and bigoted to me. As to why that's the case, it's a trickier question. I think that there's a lot of psychology going on here. And so I'll just, again, I'm not a professional psychologist, not a professional sociologist for that matter, but I will point to one thing that seems to strike me about these things. Well, to two things. One very quick thing is, as soon as something is called a movement, it's in trouble. Whether it's the atheist movement, the skeptical movement, the effective altruism movement, or whatever, when you have an idea like atheism, God does not exist. That's an idea. When it becomes a movement, all sorts of bad things can happen, right? Now, okay, there's people, you're in the movement or you're out the movement, there's good ways of behaving, there's all sorts of possibilities for things to go wrong, and they typically do. So that's one very broad thing. The other thing is that in that particular movement that we're talking about of atheism and skepticism, there is the huge danger that you are in a movement that is in large part devoted to patting itself on the back for being more rational than the rest of the world, right? You people think that there's a giant man in the sky who is judging you, but I am too rational to believe that. And I'm in favor of being rational. I think that's a good thing, trying to be rational. But it sets you up for making the mistake when someone says that something that you're doing is not rational or not correct or not nice, of not listening to that kind of criticism because you've already decided that you're more rational, right? And so people become defensive. And in fact, there's a backfire effect where they double down on whatever it is they are believing. I think that this is not specific to atheism and skepticism, actually, but in progressive liberal circles more generally, there's a certain slice of people who, feel nostalgic for the days when in their minds it was all just about the economy and class struggle, right? And they thought of themselves as, fighting for the workers and the underprivileged and whatever. And now it's about identity politics and like these black people and these trans people and whatever. They are all leaving the message that they thought was supposed to be the message. And you see the difference is that the people we're talking about here could think of themselves as the underdog when it was all about, fighting for the lesser well-off. But now you're telling me there are other groups that are disadvantaged that I'm not in. Maybe even you're implying that my group is causing the disadvantage. You're kind of criticizing me. A lot of people in these communities, like, the most irrational response you can get from them is to call them racist or bigoted or whatever. No matter what the evidence for it is, they're like, you can't believe I'm that kind of person. I'm a rational person. I'm not that. And, that leads them to some dark places when they try to justify that. So I don't know how much of the effect is caused by that particular syndrome, but I do think it's real. And of course, there's plenty of people in the atheist skeptical movement, such as it is, that are very supportive of trans people. A lot of trans people are atheists, right? So it's complicated. I wouldn't want to oversimplify it. I do think that it's much easier to preach rationality than to practice it, especially when it comes to potential criticisms of one's own worldview and behavior. Eric Stromquist says, this may be a long shot, but have you read The Problem of Molecular Structure is Just the Measurement Problem by Franklin and Seifert in the British Journal for the Philosophy of Science last year? They argue that the favored eigenstates of collections of electrons and nuclei are superpositions of all enantiomers and isomers. These are chemistry words I don't understand, by the way. Not the chiral molecules or individual isomers studied by chemists, which have less symmetry. They look at Everett, Bohm, and GRW and conclude that Everett and Bohm can explain classical molecular structure, but only due to the action of decoherence in each case. However, decoherence doesn't save GRW. No, I'm not familiar with that at all. Ordinarily, if I were not familiar with it, I would just skip over the question. But it's an interesting issue. I really want there to be experimental tests you can do to decide between these different theories. There are experimental tests you can do to decide between objective collapse models like GRW and Bohm/Everett. As far as I know, there aren't any tests to distinguish between Bohm and Everett. But I'm open-minded about still looking. There's arguments that Bohm and Everett should give the same result, but there's also arguments. In fact, there's arguments from both sides that the other side just doesn't make sense, right? So if you talk to either Bohmians or Everettians who are more or less made up their minds, and you ask them the reason why they don't like the other one, it's typically because they don't think the other one does the job of being a well-defined theory that fits the data. And of course, they think that theirs does. So anyway, none of this is specifically about electrons and orbitals and in molecules and so forth, but just to say that I can imagine something like that being true. So I've not read the paper, but I can imagine that in a theory like GRW, which is one where there's a random chance that the wave function of a particle will spontaneously localize every moment or whatever. You could show that some feature of chemistry or solid state materials physics or something like that just doesn't work under these models. So I'm all in favor of doing that. It would be very, very hard to distinguish between Bohm and Everett on that account because Bohm and Everett have the same equation for the wave function. The wave function is just obeying the Schrodinger equation. But I still am holding out hope for some subtle difference that will let us test these ideas experimentally. Will says, I have moments when the suffering and unfairness of the world feels just too much to bear. When one sees children killed by bombs or suffering from horrible incurable diseases or learns about life in crushing dictatorships or poverty, one yearns for some cosmic justice that those who suffered will be made whole one day and that all this suffering wasn't just a hideous waste. These are the moments when I would be most inclined to religion, probably as a form of wishful thinking. When you have these moments, what do you turn to? Are there philosophers or ideas that you find helpful in this regard? Not specifically philosophers or ideas. I do think that just truly taking on the philosophy that of naturalism, of the world is not guided by any external forces, it just obeys the laws of physics, and appreciating that those laws of physics and the initial conditions or whatever include an enormous amount of information that we don't have access to, and therefore there will be things happen that we don't like and can't predict and can't do anything about. I think it is possible just to accommodate oneself to those true facts about the universe. We're all going to die. Probably life itself will someday cease. I have plans for the future, some of which will turn out and some of which will not. I've had plans in the past that did not turn out. It doesn't make it any easier in the moment. When a close friend of yours is sick or passes away, that doesn't make it any less tragic and hurtful when that happens. But the fact that things like that will happen are things that you can come to grips with long before they actually do. And I don't think it's a matter of like this philosopher or this idea really helps you with that. I think that there's some combination of that understanding of the world and a kind of psychological accommodation or orientation that lets you approach that with clear eyes and do the best we can, accepting that they will make us sad when they happen. Robert Ruxandrescu says, we usually talk about electrons having their spins entangled, but why not positions? Why can't we have electrons A and B entangled such that if I measure A and find it at coordinates 1, 2, 3, then I immediately know that B is at coordinates -1, -2, -3? You can. Sure, no problem at all. In fact, that's a very, very common form of entanglement. We don't even talk about it that much because it's just so common, but the example that I often use is imagine a particle like the Higgs boson. Picking the Higgs boson just because it has no spin, so we're not worried about spin at all. It decays. It decays into an electron and a positron. And the prediction, according to the Schrodinger equation, is that if you ask in what direction will the electron be moving, the answer is the wave function spreads out in all directions. It is equally likely, because there was no spin for the original Higgs boson, so there was no orientation, no special direction of space was picked out. Equal probability to observe the electron moving in any one position. Likewise, in any one direction. Likewise for the positron. Equal probability to observe it moving in any one direction. But when you observe one, then you know where the other one is because momentum is conserved. You know exactly what the coordinates has to be for the other particle that you didn't observe. There you go. And that's entanglement. Indeed, that is more or less what EPR actually talked about in the famous Einstein-Podolsky-Rosen paper about entanglement. The idea of doing it with spins came later. It might have been John Bell, actually, who originally popularized the idea of doing it with spins. I'm not sure about that. David Summers says, I finally got around to watching Oppenheimer. In your opinion, how valid was the concern that the atmosphere could ignite when detonating an atomic bomb? Was it irresponsible to carry out the test given the available information at the time? Well, I can certainly say that the movie overhyped that particular worry. The worry did exist, or rather, let's put it this way. The possibility had been raised. There was never a time when someone did a calculation and they said, oh, this will ignite the atmosphere, okay? Rather, people suggested, like, is it possible that this will ignite the atmosphere? Should we worry about that? And they did the best they could. They tried to calculate it, and they found out that the answer was no. It would not ignite the atmosphere, so they moved on. Now, it's completely legitimate to say, okay, but there was a chance. There was a chance it would ignite the atmosphere. And how exactly confident were they that it wouldn't happen, right? Isn't that kind of important? That's very true, and it's something I'm actually very interested in and not completely clear about in my own brain, how to deal with these things that you think are very, very unlikely but hugely consequential if they happen. One of the aspects to keep in mind is lots of things, other than setting off a nuclear test, have the property that they could, in principle, cause some tremendous calamity to happen, and you don't know what the probability is, okay? When I wrote my book on the Higgs boson, the particle at the end of the universe, that was a worry, right? The worry was that by turning on the LHC, the Large Hadron Collider, we would destroy the Earth eventually. And I said, look, every time you open a jar of spaghetti sauce, pasta sauce, there is a possibility that some random mutation brought to life a terrible mutated pathogen that you are now releasing into the world and will kill all life on Earth by opening that jar of pasta sauce. Unlikely, but it's possible. And what you're doing is you're risking all of human existence by opening that jar. Is this an argument to not do it? And I think that the answer is no. It is not an argument to not do it. Lots of things are possible, but we still have to get through the day. That's not a very well-formulated, rigorous philosophical theory of getting through the day, but getting through the day is actually kind of important. So I think that I would like to actually understand that better. Paul Hess says, in the many worlds interpretation, what happens when I use a quantum computer? Is there one world where I get the right answer and some other number of worlds where I instead get errors? Is the thickness of the world where I get the right answer a function of how carefully I isolate the qubits? Well, you know, as I said this before, there's not a lot of difference between what happens in a quantum computer in many worlds and any other interpretation. The success of quantum computers does so I think that it's possible in my mind, although I don't know for sure, that there could be a principal argument made that quantum computing is an argument in favor of wave function realism. Okay, the idea that the wave function really has a physical reality to it because it's becoming entangled, it's interfering, blah, blah, blah. All these things are happening. Now, the people who are not wave function realists find this entirely unpersuasive. In fact, many people who are not wave function realists, epistemic people when it comes to the foundations of quantum mechanics, actually are in the field of quantum information. So I don't understand how they reconcile that. But putting that aside, if you think that you are a wave function realist, there's nothing in a quantum computer that differentiates Everett from Bohm, from GRW, objective collapse models, Penrose, whatever, right? That's the same kind of predictions you go along the way. The only difference is, and maybe this is what you have in mind, when you do the final measurement in a quantum computer, because a quantum computation generally starts by putting in some qubits into the algorithm and running it through the algorithm, and you get out some qubits, and then you measure them, okay? So there's a measurement process, and the measurement process is governed by the Born rule. The probability of getting an outcome is the wave function squared. And it might very well be the case that the kind of calculation you've done tells you that you will, factor a large number with really, really high accuracy, 99% confidence or something like that. And so in the traditional single world interpretation, you would say there's a chance I get the right answer, there's a chance I get the wrong answer. In Everett, you would say there's a world in where I get the right answer and a world in which I get the wrong answer. And of course, to make sense of it, you have to believe that the Born rule still works. So if most of the amplitude is on the right answer, then that you interpret that as saying that the probability of me getting the right answer is given by the amplitude squared. So again, I don't think that Everettian attitude towards quantum mechanics says much or is much informed by the success or workings of quantum computers. Nanu says, I recently had the pleasure to read your paper, Reality as a Vector in Hilbert Space, and truly enjoyed it. I read it over and over again. I was wondering what was going through your head when you realized that reality is a vector in Hilbert space. You know, I feel bad sometimes because people ask me questions, just like we had the question just a second ago about like what philosopher or what idea helps you through this. I just think differently than other people do, maybe, or at least I think differently than other people want me to think. Because there seems to be this feeling like that there should be epiphanies and moments. You go like, this is the moment I realized something, or I read this book and this book helped me realize something, or this person is very brilliant and I would, here's the list of people I would like to talk to who are dead, but I would really like to talk to them because they're brilliant people. And I just don't think that way, honestly. Like it's much more gradual and process-oriented in my head. There was not a moment when I realized that reality is a vector in Hilbert space. It kind of creeps up on you. You think about quantum mechanics and you try to understand quantum mechanics, and then you think about interpretations of quantum mechanics and you decide that the Everett interpretation is a good one, and you realize that the Everett interpretation is really not about many worlds. It's about just the wave function, the vector in Hilbert space, always obeying the Schrodinger equation. And then you say, well, okay, what is it? What are the data that define a quantum mechanical theory? Like, what do you have to put into it? And you ask people and they tell you, oh, we have to give an algebra of observables and all these things. But then you think about it and you realize, no, you really don't. It might be convenient and it might be important if you are devoted to some notion of locality in your theory. So in quantum field theory, we often care about algebras of observables and things like that. Local observables is usually implicitly taken for granted there. But really, you understand that the quantum theory simply is a theory of a vector in Hilbert space obeying the Schrodinger equation. You come to that understanding gradually. So nothing was going through my head in that moment because that moment didn't exist. Many, many things went through my head along the way to it. And I hope that things keep going through my head and I come to new understandings. And it's going to be a very I don't want to say scattershot process, but there's always a process. It's a give and take. You go back and forth. Things become clear, less clear, etc. That's how life goes, at least for me. Colin Johnson says, what proportion of baseline reality do you think we currently perceive? We certainly don't perceive everything right now, as indicated by our need to use advanced tools to view different parts of the electromagnetic spectrum. Similarly, we don't perceive nothing, or we wouldn't be able to predict as many things as well as we do. So on a scale from 1 to 10, where are we today? I hope you don't mind if I say that this is an absolutely impossible question to answer. Like, there's no such thing as the measure on how much of baseline reality we currently perceive. Let's put it this way. When I look at this table in front of me, this poor table is going to get overused as an example, but I could tell you facts about the table. I could tell you its approximate size, its color, its shape and things like that. But there's, who knows, 10 to the 26 atoms in this table, and I'm not telling you nearly that much information. So on a scale of 1 to 10 of how much I'm perceiving of baseline reality, I'm kind of perceiving 1 plus epsilon, where epsilon is 10 to the minus 26 or something like that. I'm not seeing neutrinos. I'm not seeing most of the photons. Most of the photons emitted from the table aren't headed toward my eyeballs, right? They're going in other directions. So yeah, most of reality I'm not perceiving. Not to mention the fact that I'm in a room, which is a infinitesimally tiny fraction of the whole space of reality. I don't even have my window open, so I can't even see the outside world right now. So that's okay. We directly perceive a very, very, very tiny slice of reality. And the interesting thing is that it's enough to do pretty well, right? To have a pretty good handle on how reality works, a causal map, as Judea Pearl would have said, about if I poke something in one way, what its response is going to be, despite the fact that I know very, very little. The miracle of emergence, that's what it's all about. TJ McMorrow says, in several podcasts, you've distinguished between the concept of complex and complicated systems. In some of those episodes, you and your guests have discussed ways of defining or at least describing complex systems. I'm wondering whether it's more straightforward to define complicated systems. I recently learned about the notion of Kolmogorov complexity, and it seems like a pretty good measure of how complicated a system is. In plain English, both seem to roughly mean how much information is required to write down the full rules of the system. Is that a reasonable connection to make? I'm in favor in these kinds of questions of not saying that there's a right answer. There's many different aspects to what you mean by complexity and complicated. I think it's a wrong strategy to say, here is a word like complex or complicated. Let's try to decide what it means. That seems to imply that the meaning of the word pre-exists our use of the word out there in the numinous ether or something like that, and that doesn't quite jibe with how I think it actually actually does happen. I think that what happens is we can ask that we use a word, we use the words long before we rigorously define them, and then when it comes to rigorously defining them, we realize, actually there are different aspects that we're using the same word to convey. So in the case of complexity or complicatedness, I'm not even going to differentiate between them for these particular discussions. There is something called Kolmogorov complexity, the length of the shortest program that would output the system or the string of digits that you're talking about. Scott Aronson and I, when we wrote our coffee cup paper, defined something we called apparent complexity, which is the Kolmogorov complexity of the coarse-grained version of the image or the system you're talking about. Both of those are just descriptions of either a string of bits or of some configuration of matter in space. But there are many more things you would like to attribute complexity to, including processes, right? Charlie Bennett defined an idea called logical depth, which is not the length of the program that would output the string, but the time it would take to run the program that would output the string. There's other measures of complexity having to do with calculations or computations, right? How long does it take to solve the traveling salesman problem? But when it comes to physically moving things in the world, things that have many parts, like a human body, okay, the complexity of the human body is not simply encapsulated by the distribution of its parts through space. We talk about the processes that go on in the human body, the creation of ATP and the traveling of white blood cells that Jim Allison talked about through the body to fight diseases and things like that. So it should be the least surprising thing in the world that there are different ways to quantify what we call complexity. And the word complicated is generally not a technical term that people use in this context. So when I say that complexity and complicated are different, what I really just mean is that we have an informal notion when things are complicated. We have several different formal notions of when things are complex. And if you really want to be careful, you should tell me what version of complexity you're referring to when you say something is complex. Matthew Fritz says, is the Dirac equation just a special case of the Schrödinger equation? I remember learning that the Dirac equation is the first successful relativistic treatment of quantum mechanics. But you generally talk about the Schrödinger equation as being the equation of quantum mechanics. Yes, that is completely true. I am completely right about this one, even though there's sort of a lingering set of places where you could hear the wrong answer about this. So the story is, of course, in fact, people don't usually tell the story. The story is that Schrödinger knew about relativity. When he wrote down his equation, the Schrödinger equation, he wrote down a non-relativistic equation. But he knew about relativity perfectly well. He first tried to write down a relativistic equation. And he came up with, I'm pretty sure he came up with basically what we now call the Klein-Gordon equation, which is a relativistic wave equation. It just doesn't fit the data if you try to solve it for electron energy levels, et cetera. So he eventually found his non-relativistic equation. And what happened was Klein and Gordon tried to find a relativistic equation. So did Dirac. They were aiming at different things. Dirac was aiming at the electron, which has spin. It is now what we call a fermion. Klein and Gordon, their equation turns out to describe scalar fields, scalar particles, which were not known to actually exist at the time, but theorists could talk about them. But they're both perfectly relativistic. Neither one of them is a generalization or a replacement for the Schrödinger equation. They're very useful in physics, but for a completely different purpose. The Dirac equation and the Klein-Gordon equation are both classical equations of motion for fields. The Klein-Gordon equation is the classical equation of motion for a spinless field. The Dirac equation is the classical equation of motion for a spin-1 field that has electric charge. Okay, so it includes both the electron, spin up and spin down, and the positron, spin up and spin down, the particle and its antiparticle. So Dirac thought that he was generalizing the Schrödinger equation, but it turns out that that's not what he was doing. Okay, so the correct interpretation, and people sort of hang on to that mistake. It sounds good when you say, well, there was Schrödinger and he had the non-relativistic thing, and then Dirac came along and he made it relativistic. The relativistic thing is quantum field theory. That's what the relativistic thing is. But even in quantum field theory, you start with the classical field, and Dirac and Klein and Gordon gave us equations for those classical fields, and then you quantize it. And there's different ways of quantizing the field. And one way is precisely analogous to what Schrödinger did for a single electron, namely to invent a wave function that is a function of the field rather than a function of the particle. And that wave function obeys an equation, and that equation is called the Schrödinger equation. The Schrödinger equation is completely general in terms of, does it describe non-relativistic things, relativistic things? Yes, there are different versions of the Schrödinger equation that apply to any of those individual circumstances. Indeed, there's a version of the Schrödinger equation that applies to a single qubit, right? A single degree of freedom that is either spin up or spin down, which is not a field at all. For every quantum system, there is a Schrödinger equation, even for the relativistic ones. Supine Otter asks a priority question, continuing in the spirit of asking someone who doesn't like tattoos about tattoos. You previously suggested your favorite equations to ink on one's body, but for the visually inclined, can you recommend the physics-related diagrams or images that are most meaningful, satisfying, or beautiful to you and would make a great tattoo? It's a good question, a perfectly legit question. I'm going to probably not give you a great answer just because, well, anyone who gets a tattoo shouldn't listen to me about what tattoo to get, and not because I don't like tattoos, because they shouldn't listen to anyone about what tattoo to get. They should think of it themselves, all right? I mean, different, like, do you care about thermodynamics? Do you care about general relativity? Do you care about quantum mechanics or whatever? These would all suggest different tattoos you could get. I mean, you could be playful. You could get a tattoo of Schrödinger's cat, right? Of being both awake and asleep at the same time. You could get a tattoo of a space-time diagram. There's some very nice Penrose diagrams, like the Penrose diagram for the eternal Schwarzschild black hole is a very nice little diagram, pretty simple. You could shade it in if you wanted to make it look a little more complicated or something like that. I mean, honestly, leaf through books and papers by Roger Penrose, because he is not only a great mathematician and physicist, he's a great artist as well. And he always has these amazing diagrams in his papers. So if you're a relativity kind of person, I would definitely recommend looking through Penrose's work for striking images, because they're definitely there. And you could go either, more whimsical, like the Schrödinger cat thing, or Laplace's demon. Get a tattoo of Laplace's demon. I don't know what Laplace's demon looks like, but you know what I mean. Feynman diagrams, particles interacting. Feynman diagrams can get pretty complicated. So they don't have to be simple ones. So I think there's all sorts of different possibilities. If nothing immediately strikes you, I like the idea of leafing through some technical physics papers. Even if you don't understand what the papers are about, maybe you can understand like the area they're in. Are they in quantum cosmology? You can read the papers by Hartle and Hawking. See if there's any images in there that strike your fancy, and that would be something that would be pretty unique. David Whittaker says, the universe is expanding and the stars and everything else are moving away from us, at an increasing rate even. But they can't all be moving away from us or we'd be at the center of the universe. And if they are moving away from us, but everything started together immediately before the Big Bang, why is everything not traveling outwards at the same speed? The great thing about this question is that the second part answers the first part. If everything was traveling outwards at the same speed, that would indeed be an indication that we were at the middle of the universe, but it's not. So forget about moving. Forget about, visualizing everything moving away from everything else. Think about, the universe itself. In fact, what I like to do is to literally imagine you're outside on a clear night and you are gifted with perfect vision, including for very, very distant galaxies, okay? So we're not using any analogies. We're just trying to visualize the real universe. And imagine that you have Doppler imaging in your eyeballs, so you can see how fast the different galaxies are moving away from you. And you notice that galaxies that are relatively nearby are moving away from you relatively slowly. Galaxies that are far away are moving away from you faster. Okay, so they're moving away from you at different speeds. What does that mean? That means that if you think about the people who are living in one of the nearby galaxies, they see you moving away from them in one direction, and the galaxies that to you are further away are moving away from them in the other direction. Indeed, they see the same kind of pattern that you do. They see everyone moving away from them in a pattern which is the further away they are, the faster they're moving. So this precise behavior, where everything is moving away from everything else with the property that further away things are moving away faster, is exactly what you need to not have a center, so that everything is created equal. Everyone sees the same basic kind of thing. This is both what is predicted by general relativity and what is actually observed in the universe. Anonymous says, imagine a future where the NBA moves to a virtual format and all players are linked to an avatar via a brain chip. All avatars are the same height and strength. Do you think the majority of current players would stay in the NBA, or are there probably lots of more skilled, smart basketball players out there who simply aren't large or genetically fortunate enough to compete? I think that it depends on whether you're talking about the very short term or the very long term. I think in the very long term, if everything is virtual and everyone's physical abilities are essentially equal, then I think that I'm guessing, this is an empirical question you'd have to test, but my guess is that the distribution of basketball talent is kind of uncorrelated with height and physical speed and things like that, and you get all sorts of people doing very well. It's basically playing a video game, right? There's not any, as far as I know, correlation with height and strength with ability to play video games, okay? But if you did this and did it next year, then I think what you would find is that the current very good basketball players would still be the very good basketball players because they've been training for a very long time to do exactly this and in ways that other people haven't. If you're a casual basketball player, you haven't been putting in the work compared to an actual NBA player. Some NBA players would not turn out to be very good. There are some who are just coasting by on their physical gifts, and they would not do that well. But I think a lot of the actual basketball players, to stay and flourish in the modern NBA, you have to be pretty talented and dedicated. You know, there's always going to be exceptions. I remember just because of a similarity in names, there was a center in the NBA back in the 80s named Joe Barry Carroll. No relationship to me, but his important talent was he was tall. That was it. So his nickname, Joe Barry Carroll, was nicknamed Just Barely Cares because he was really not interested in putting in the work, getting better. He was just standing out there and being tall, and he earned a lot of money doing that. I think it's harder to do that now, maybe, than it was in the 80s. Josh Flowers asks a priority question. Do measurements made in light years need to be adjusted to account for velocity changes between a photon's initial reference frame and its destination reference frame? You know, in principle, sure. I mean, you have to be careful when you're talking about distances of objects in astronomy because there is no fixed reference frame, okay, with respect to which we're supposed to measure these distances. As Einstein taught us, if you're moving close to the speed of light, the distance that you think you would have measured if you had not been moving close to the speed of light might be very different. It's length contracted, as we say. But the good news is that, in fact, the amount of velocity that typical astronomical objects have, galaxies and stars and planets and things like that, is small compared to the speed of light. Even though there's not absolutely a reference frame in physics, there is approximately a rest frame in the universe, where stars and galaxies typically move at about 1/1000th the speed of light with respect to each other. So the Doppler effect is actually just not very big. There are circumstances in which it matters. In fact, there's a phenomenon called the finger of God. And the finger of God is this. If you have a cluster of galaxies, okay? So you have a cluster of galaxies, and that means you have a bunch of galaxies, and they're orbiting the common center, which means that some of them will be you're measuring two things. This is back in the day. You weren't measuring the distances directly. You're measuring the redshift and using that to infer a distance to the galaxy. And then you can accurately measure its position on the sky, right? Its angular position on the sky. So your inferred distance measure to the galaxies is contaminated by the fact that the galaxies are moving. You're measuring the redshift, and some of that, not most of it, just a small amount, but some of it is from the Doppler effect. And that Doppler effect that affects the redshift and therefore your inferred distance only is added to the distance measure radially, that is to say, in the direction of your line of sight. The angular distance you just measure by taking a picture of the galaxies on the sky. So you have accurate measure of where the galaxies are in the sky and a distorted measure of where they are along your line of sight. So you take what should be a relatively spherical blob of galaxies in a cluster, and when you plot it in what you think is position in space, it is elongated in the direction of you. It's the finger of God. The joke was, this is a finger of God pointing at you saying, you are wrong, because you have small errors in your measure of distance. Now, this was a thing back in my day, in the early days of my cosmological career, because measuring galaxies and their redshifts and their distances was a painstaking process, and we didn't have a lot of them, and therefore the ones we had were relatively nearby. As you go to further and further clusters of galaxies, etc., the relative importance of this Doppler effect becomes less and less because the overall recession velocity becomes more and more dominant. So these days, this kind of thing is not that important in terms of making maps of galaxies, and even its existence is perfectly well understood, and there are statistical techniques for compensating for that mistake. So yes, these differences exist. No, they're not very big. Yes, even the small differences are things that we know about and are able to compensate for. Alex Reinhardt says, why do you think that complexity science concepts have caught on in a popular way, especially chaos theory, but also things like economic examples and flocking, but aren't captured in most STEM university educations? This is just my perception. Yeah, I think your perception is kind of right. And I think that there's a couple things going on. I guess the biggest thing is David Krakauer and I disagreed about this when we were talking, so you can go back and hear our conversation. He's the world's expert on complexity. But I kind of think that complex systems science is still pre-paradigmatic. That is to say, we don't have a fixed curriculum, a fixed set of examples, a fixed path from not knowing anything to here are the basic things you should know and here are the applications of them, right? In physics or economics or chemistry or whatever, we kind of agree on what is the first course you should take, the second course you should take, and you build up an agreed upon set of knowledge. With complexity, it's still more of a grab bag. There's very interesting results out there. There are some things that seem to be common across different kinds of complex systems, but it's less clear what exactly the standard set of knowledge is supposed to be. It's more scattered across different domains, different disciplines, and therefore harder for it to get into a standardized curriculum. We're getting there. There's a couple of very interesting textbooks that now exist on complex systems theory, and maybe it will become more popular. But also, the way that complex systems, I never know whether to call it complexity or complex systems, and therefore the accent on the first word is always unpredictable for me. Complex system science is an interdisciplinary science by its very nature. It's what can be a complex system? A biological organism can be a complex system. The economy can be a complex system. The internet is a complex system. A language is a complex system. What department is this supposed to be in, right? Who is supposed to be learning this and teaching it? So what you get is different departments doing little bits of it, and it hopefully in some areas does have an impact, but there's no standard, there's no consensus. And I think that maybe that will change. I keep trying to teach a course in complex systems in the physics department at Johns Hopkins. And it's not like they're trying to prevent me, but other courses that are more pressing keep coming up. So I'm teaching quantum mechanics next year. That's got to be taught. Someone's got to teach quantum mechanics, and so I'm going to be doing it to the undergraduates. We do have a new faculty member at Hopkins, Matthew Wyart, who is a true complex systems statistical mechanics expert, and he's going to be teaching things. So I do think that, maybe it's seeping its way in. These things take time. Academia is very slow. They're very slow to change and to adapt to new ideas. Bjorn Haig says, you seem to be able to disagree with people so gently, clearly, and unobtrusively. How do you do it? Are you even aware of this being a skill of yours? Yeah, I would disagree that this is a skill of mine. I don't think this is a skill. That's not the way that it comes across to me. I get very frustrated with people sometimes, and I do disagree with them maybe a bit too harshly or shrilly than really I do. I try to disagree gently and constructively. It's not about being unobtrusive or even gentle so much as clear. Clear is important, to be clear about why you disagree, and to be constructive about it, to try to understand why we're disagreeing, maybe move forward. But I would say that there are different kinds of disagreement, right? There are people who are worth disagreeing with, and there are people who are not worth disagreeing with. I do try very hard to not spend too much time disagreeing with the people who are not worth disagreeing with. I mean, I disagree with them maybe, but if they're not going to change their minds or their thoughts are just not very interesting or good, then I'm not going to spend a lot of time engaging with them. I'm trying to engage with people who I disagree with in a way that potentially they could change my mind or I could change theirs, or at least we could learn something important from each other. That's the criterion that I try to have for guests on Mindscape. It doesn't always work, There's podcast has to happen every week, and I choose a lot of different people. But basically what I'm looking for is somebody I can learn from. Even if it's something that I already know a lot about, I can learn little details, and the audience maybe can learn a lot. And if it's something that I disagree with somebody, but I want to know why they think that, right? So I'm choosing to engage with people I disagree with, but can learn from, and so that kind of naturally makes it a more pleasant experience. I do think this might not be true, but I think that it's weird to me to see people on the outside of academia be less able to disagree with each other politely and constructively than people inside academia. If you just asked me, if I hadn't thought about it that much, and you just asked, do professors disagree with each other sort of loudly and emotionally, I would say, yeah, they really get into it and they disagree pretty badly. But still, almost all the time, not all the time, but almost all the time, professors, intellectuals, scholars, people who are in academia, they disagree, and they go out and, have a drink with each other and talk about it. They keep talking about it forever, for decades, right? This is very, very standard. It's not 100% by any means, but it happens all the time. And I think that a lot of people outside just, if they're disagreeing, then that person is an enemy. And they shouldn't be engaged with in any way. And that's a little alien to me. It makes me sad when I see things like that. Folkman says, I just finished reading The Big Picture, which I found excellent. On the question of free will, it almost seems as if your definition results in a situation where entropy is reversed or inverted. Multiple potential macro states resulting from the decision you actually make, you have free will so you can make many different decisions with distinctly different outcomes, correspond to only one microstate, which results from the deterministic chugging forward of the microscopic configurations based on the laws of physics. What are your thoughts on this interpretation? Does this have any interesting implications for the arrow of time and related concepts? I'm not exactly sure what you have in mind here. I'm not sure that it came through to me perfectly clearly, but I don't think that your interpretation is on the right track. Let's forget for the moment about quantum mechanics, okay? Quantum mechanics introduces true indeterminism into our observed world. So that's something that in detail, at the detail level, we have to keep in mind. But even in classical mechanics, if classical physics were true at the base level, you would still have a world, I think, you could imagine a world that looks pretty similar to the one we live in, where we're made of atoms and the atoms are jiggling around and doing different things. And the point is, in that world, when you have emergence at a level of, there's a higher level where you've coarse-grained over a lot of individual details, and at the lower level there's deterministic microscopic dynamics, it will often be the case that the higher level dynamics are stochastic. The best possible thing you can do is make a prediction about probabilities, even though the lower level dynamics are completely deterministic. If I have a theory of, when a volcano is going to erupt, the details will depend on a lot of microscopic facts that I don't know the answer to, right? But the point is that what that means is there are two, actually many more, but let's say particularly two microstates that are in the same macro state that lead to very different behavior at the macro level. So there's a microstate of the volcano. I look at the volcano, I do all the tests I can, but I cannot measure every single atom in it. So there's details about the pressure and the temperature that I don't exactly know. Certain microstates of the volcano are going to explode any minute now. Other microstates of the volcano are going to last years without exploding, okay? So that's okay at the emergent level. That's not a failure of emergence. It just means that the emergent theory tells you the probability that the volcano is going to erupt. And I think the same thing is true with people and with free will. My macro state description of a person obviously doesn't include an enormous amount of information about the details of what's going on in their brains, right? So it may very well be the case that the microphysics of what's going on in their brains completely determines what they're going to do next, but that information is not available to me. I don't have that information. I don't even have that information about myself, much less about other people. So what happens is in the macro state that I use to describe a person, there are various different possibilities about what will happen in the future. And 100% compatible with everything I know, there are different possible future choices. We call these decisions or, choices, decisions, things that your free will is doing. And free will is just a label we put on them. And I know that some people don't want to put that label. That's fine. I don't care. Don't put it on. I'm just trying to correctly describe what goes on in the world. Henry Jacob says that so many people support Luigi Mangione, which blew my mind, suggests that a lot of people are consequentialists. Do you agree with this inference? So Luigi Mangione is the one who killed the CEO of United Healthcare, which did indeed start a lot of conversation there on the old internet and elsewhere. I think that here in the United States, for those of you who don't live here right now, we have problems with our healthcare system. And a lot of the problems in the United States in general are simply the result of the fact that very important functions of everyday life are outsourced to corporations who are trying to make as much money as possible, not trying to make our lives better as possible. The whole idea of capitalism and Adam Smith is that under certain circumstances, the interests of corporations trying to make money and the interests of the consumers or the workers can align with each other, right? You can actually have a situation where it's win-win for everybody. But that's not inevitable. This doesn't necessarily happen. Sometimes the corporations can just leech off money from people because they have figured out a way to do it. It doesn't make anyone's life better, except they make money. And the insurance industry here in the United States is a classic example of that. And so it's in a regime, or it's in a context where emotions run very high because you're literally talking about people's lives, people's health. The healthcare companies deny life-saving care to people, and so people are rightfully angry about this. And so Luigi Mangione took it out. I don't know the details. I don't follow this kind of thing very carefully, but he was someone who was upset about the situation. I think that there were personal issues involved also, and he basically assassinated the CEO of a healthcare company. And there was, among things that I see on the internet, there was a remarkable amount of cheering him on after the fact, with the very basic justification that, look, this healthcare CEO, in fact, was responsible for many more than one deaths in a very tangible way. And I think that there's a couple things going on. Consequentialism might be part of it. So Henry is suggesting, well, you can kill one person, but then you're saving many other people. So it's sort of a trolley problem kind of thing, and maybe that's okay. I don't actually think that that's really what's at the heart of the support for something like this. I think it's just more visceral, right? People feel powerless. People feel like bad things are happening and they can't do anything with it. And this is when people think about turning to violence. It's not a good sign, I don't think. I'm not in favor of assassinating the CEOs of healthcare companies. I think it's bad for all sorts of reasons. It would be a long list of reasons why it's bad. But aside from the consequentialism argument, the other argument that I think is perfectly legit is to say we count different kinds of deaths differently in terms of being upset by them, thinking of them as illegitimate, et cetera. If someone takes a gun and walks up on the street and shoots somebody, then we all agree that's bad. But if someone sits behind a desk and judges that a person doesn't deserve to get health care, that's just business as usual, right? That's just how the system works. And I'm entirely on board with arguing that we should think about these kinds of deaths in more similar ways rather than in the very, very different ways that the system currently does think about them. Doesn't mean I think we should go around assassinating people. I'm kind of a believer in the rule of law, not in vigilante justice. But I do think that taking seriously accusations against people and corporations whose actions end in deaths of ordinary citizens is something we absolutely should be able to do. Not that I really know how to bring it about, but that's true for many political or social or economic ideas. Kevin's Disobedience asks a priority question. I'm a contractor by trade, but a year ago, I decided I wanted to teach myself particle physics after work. In short, I quickly realized I needed to go back and relearn at least some basic classical mechanics before moving on to relativity and quantum mechanics. So I'm slowly working through a high school textbook again. But after reading dozens of popular books, the thing that impresses me the most about physics is physicists mastering the old and new stuff to work on the cutting edge. So my question is, would graduate-level problem sets on, say, geometric optics or thermodynamics be simple to you now, or would it involve a quick refresher? I guess I'm curious how much of the technical education one retains and in what form. I hope that's clear. It is clear. So putting aside all the details that might come up in your mind in the preamble to the question is, once you're a professional physicist, can you go back to the stuff you did as undergrad or graduate at the problem set level, and is it all now easy, or do you have to work just as hard? Well, there's two things involved. One thing is sometimes these problem sets in thermodynamics or E&M or quantum mechanics or whatever just involve a lot of work, right? Sometimes there were a lot of all-nighters back then when I was in grad school. The amount of calculations you have to do is just large no matter who you are, no matter how much knowledge you have, right? You got to do that integral. You got to solve that differential equation. You got to diagonalize that matrix, whatever it is, okay? So some of it is irreducible, the amount of work you have to do. So that's one thing. The other thing is, of course, hopefully you do get better at seeing how to solve these problems. Sometimes I will see online I'll see a final exam or a problem set in a course that is being taught somewhere else, and I haven't taken it for many years, and I read it and I go, oh my God, I would never be able to solve that. But then I sit and think about it and go, actually, yeah, no, I could do it. I just haven't thought about it for a long time. And I think that it's a combination. You do forget some of the details that you might have recently learned if you're taking the class. But I think that, in fact, the purpose of the education, this is a slight exaggeration, but a lot of the purpose of the education is to sort of know where to look. Like, oh, okay, this particular problem requires taking a Fourier transform, right? Or this particular problem is a perturbation theory problem. Like the angle of attack and, what books you have to turn to figure out what equations you need and that kind of thing. Rather than the actual solution to the problem or even the actual step-by-step way to solve the problem, it's more like, what kind of problem is this? What kind of tools are you going to need to do this? That kind of stuff is taught to you, and it's not necessarily what you think is being taught to you, but it's what sticks with you decades later. So I would say that specifically, it would not be simple for me to answer a question like graduate level statistical mechanics or something like that necessarily, but it would be much simpler now than it was back when I was doing it the first time. Anders says, so it turns out that Schrödinger was a pedophile. He groomed a 14-year-old girl and got her pregnant when she was 17. He also attempted a relationship with a 12-year-old girl and called her the love of his life. How do we handle situations when unquestionably brilliant men are monsters? Should we mention it in the textbooks? And when lecturing, should we rename lecture halls and remove statues of them? I think, I chose this question to talk about because I don't think the answer is easy. I think it's a complicated one. I don't think there's a cut and dry solution here. I do think that we shouldn't hide it when people who are great for one reason are pretty terrible for another reason. And I think that for Schrödinger, that's a perfectly plausible conclusion to draw from his actions. I don't think we should rename the Schrödinger equation. I think of these labels, I think of names of equations and things like that as labels, not as honors. Sure, Schrödinger is someone we remember in part because his name is on an equation, but it's also just the Schrödinger equation. That label, the Schrödinger equation, has transcended Schrödinger the person a long time ago. But in terms of like honoring them by statues and things like that, that's a more difficult question. I think that on the one hand, the argument would be we're honoring them for the good work they did. The other argument would be like, shouldn't we be honoring good people rather than bad people, not just people who achieve things no matter how bad they are? I think I don't know the answer to those questions. I do think we should be upfront about it. I think that there is a certain temptation to think that because somebody did a great thing in science, or for that matter in art or politics or sports or literature or whatever, that there are heroes and we should honor them, right? And that I'm much more skeptical about. I think that that's always a dangerous thing because you're honoring someone who you don't know personally, right? If you want to honor the thing they did, that's fine. But then to just transfer that into honoring the person as a whole when you really don't know that person as a whole is a very dangerous move. So I'm in favor of teaching the history accurately and letting people go where they will from that. Natalie Standing asks a priority question. I'm a 52-year-old with a passion for reading about physics. I've been captivated by your books and those by Brian Greene. They never fail to blow my mind. Though I didn't excel in school, particularly in mathematics, I find myself fascinated by the discipline. I would love to deepen my knowledge of this beautiful language. Could you recommend some starting points or resources to help me on this journey? Well, I'm going to recommend my own books, right? That's where I'm going to start. But let me say, books are for some people. Videos are for other people. Classroom discussions are for other people. Different people are going to learn different ways. You got to find the way that works for you. Some people are mostly happy just reading the texts. Other people need to work out problems and things like that. Again, find what works for you. Part of the goal of my hopefully eventually completed trilogy on the biggest ideas in the universe is to provide some insight into those more quantitative aspects of modern physics that popular level books don't cover, whether it's classical mechanics, quantum mechanics, or complexity and emergence. So to me, that's like hopefully a very good starting point for exactly what you're thinking about, the biggest ideas in the universe. Leonard Susskind also has a series of books, The Theoretical Minimum. It's a little more straightforwardly course-like laid out. In the biggest ideas, I try to sort of mix and match things. I don't go in the traditional order because I'm very, very explicitly not teaching a course, right? It's about people picking up the books and reading them. So it's a slightly different angle, but, very similar spirit of showing you the equations and helping you learn about them. None of those books are quite at the level of a textbook. So, ultimately, if you really want to learn this stuff, well, what do you mean by really want to learn this stuff, right? If you want to learn it at the level of a professional physicist, you have to start at the beginning. You have to learn classical mechanics and calculus and differential equations and waves and E&M and basic quantum mechanics and statistical mechanics, and then on your way up. There is a famous/infamous web page put up by Gerard de Tufte, who is a Nobel Prize-winning brilliant physicist, called How to Be a Good Theoretical Physicist. And he lists, I've always thought that maybe I should do my own version of this, because de Tufte lists every course you need to take. And he points to specific resources, both online and textbooks, that will take you all the way up through, quantum field theory and particle physics and condensed matter physics and so on. But he also, has all the steps along the way, including things like foreign languages and the mathematics and so forth. The problem is that de Tufte's idea of what you need to know is rather expansive. So it's incredibly intimidating. Like you look at the list and you're like, I'm never going to get through all this. And, maybe that's what you need to be in a Tufte level theoretical physicist, but maybe some of us want to just aim at being a working class hack theoretical physicist, and that would be good enough. So you can maybe pick and choose a little bit, but ultimately, you're going to have to buy some textbooks, I think. Maybe buy is the wrong word, because at this point, there's so much stuff online, whether it's online courses, which I really am a fan of, or online lecture notes or whatever. I don't have specific recommendations there, but go to edX and Coursera. These are online course sites, or go to Khan Academy or whatever, and just find courses you can sign up for. And many of them are archived, so the videos are there. You don't need to take them at some specific pace. You can just do it whenever you want, which is great. Christoph Radomski says, in Space, Time, and Motion, you mentioned that you, being a science consultant in Marvel's Thor, had something to do with Jane Foster's mention of an Einstein-Rosen bridge. Are you also responsible for Tony Stark's mentioning quantum fluctuations at Planck scale triggering Deutsch proposition in Avengers Endgame? No, that one was not mine. There were other science consultants on Endgame. I think I'm not 100% sure, but I think that former Mindscape guest Clifford Johnson was one of them, and it might be from him. I mean, that particular statement of Tony Stark's is kind of word salad nonsense. All the individual terms make sense, but the particular way they are arranged in order doesn't, that's fine. It could have been better. Like if they had, had more science consulting going on, it could easily have been massaged into a statement that both made sense and served the dramatic purposes in the moment. But, despite the fact that these movies cost a lot of money to make and spend a lot of time being made, there's always kind of a rush. People don't have time to sit back and go like, okay, how exactly should we get this one particular line? Should we get the technobabble right so that it makes sense? So no, I'm not responsible for that one. Sorry. Gary Miller says, I believe that who I vote for president has no impact on who gets elected. Even if I convinced 10 or 100 friends to vote the same as me, there would still be no impact on who gets elected for president. But if you read this question aloud to your entire audience and agree that any one person's vote doesn't matter, you risk alienating a large group of people from voting. It seems like democracy depends on people believing something untrue, that their vote matters. Is this an inherent problem with democracy? Well, there's certainly some problem with democracy that you have two choices. Either you let voting be voluntary, which happens in most places, and then some people don't do it, or you make it mandatory, and then you're going to have voters who are hilariously underinformed. And in fact, that still happens when the voting is voluntary. So I don't think there's any perfect solution to these questions. I don't think it's right to think of democracy as trying to be a method for making the best decisions. It's trying to be a method of giving people a voice. And of course, any one person's voice is small in countries that are as large as ours. I think an underappreciated problem with democracy is just that nations are big now, right? I mean, 200 years ago, we didn't have 300 million people in the country, and the voices mattered a little bit more. So there's a lot of things going on here. We talked about this with Herb Gintis, among other things, and it's a reflection of a more general issue in philosophy, in moral philosophy or whatever. So Immanuel Kant would tell you should act, if you want to act morally, in such a way so that your actions may be the basis for a general principle, right? In other words, the golden rule, basically the golden rule. The categorical imperative is a slightly philosophized up version of the golden rule. It says act the way you want everyone else to act, right? But why? Why should I do that if it's not actually true that everyone else will act the way that I'm supposed to act? Why should I be acting in that way? Now, of course, counterfactually, if everyone acts the way they want everyone else to act, then they will all inform themselves and they will vote, et cetera, et cetera. So even if that doesn't happen, should we act because we want it to happen in the way that we would be acting if it were happening? That's the question. And the answer is not obvious. The answer is not obvious at all. I mean, Herb Gintis's answer was something like it's kind of tribal affiliation, signaling, right? We don't vote thinking that our vote will be the tiebreaker. We vote thinking that we are expressing ourselves. We are saying, here is who I stand for, where I want the country or the municipality to go, things like that. And it's rational in a way that is different than how we pretend it's rational. We pretend it's rational because we're choosing who is going to lead us, and collectively that happens. But at the individual level, the rationality is about belonging to a group, not about making a decision. Does that hang together? I really don't know. I do think that there's a give and take between our individual actions and how we influence others. So therefore, I am very much in favor of both voting and encouraging other people to vote. Chris A. says, why is developing a quantum description of gravity so difficult? A lot of very smart people have been trying very hard for nearly 100 years, so what is it about the problem that makes it so intractable? It's a great question, one that does get talked about, but maybe deserves to be talked about more. And I think that there are two kinds of problems. This is not just me. I'm not just making this up. There's a standard understanding that there are two kinds of problems with quantizing gravity. There are technical problems and there are conceptual problems. The technical problems are just that according to the ordinary ways we have of doing quantum field theory, which is what you should need to do in gravity, since Einstein's general theory of relativity is a classical field theory. In quantum field theory, we have rules for taking a classical field theory and quantizing it. And in the case of gravity, these rules don't work. The straightforward way of saying is that it's not a renormalizable theory, which is to say that if you try to extend your quantum field theory version of gravity to arbitrarily high energies, you kind of get nonsense. You lose the ability to predict what is actually going to happen. Okay, I'm sort of hesitating because there's a technical way of saying this. I'm not sure if it's worth saying, but essentially, to make any one prediction requires an infinite number of input parameters in the theory. That's the consequence of non-renormalizability. Now, you may have heard me say that we have this thing called effective field theories, right? If you don't want to extend your field theory to arbitrarily high energies, then we can just say we have a cutoff, we have an energy scale above which we don't care, and make a theory about what happens below that scale. And that you can do for gravity, and it works in a wide variety of circumstances. But if you think that what we're actually after, at some point, you care about what does happen even at arbitrarily high energies. So the effective field theory technique lets you have a functioning theory, an effective theory, below a certain energy scale. But that doesn't mean you don't care what happens above the energy scale. And when you start including gravity, maybe you do care what happens at that energy scale. So gravity is just sort of not a successful quantum field theory by the standard measures. So in other cases where we had like the Fermi theory of the weak interactions, Enrico Fermi came up with this theory where neutrons could decay into protons, electrons, and antineutrinos, right? That's a non-renormalizable theory also, just like gravity is. But it turns out it wasn't the right theory. It was only a theory that works below a certain energy scale. And above that energy scale, you have to invoke W bosons and the weak interactions and things like that. And you get the standard model of particle physics, which is a renormalizable theory. So you might hope to find a renormalizable theory that reduces to gravity at low energies. No one has been able to do that. They've tried. Okay. Well, actually, sorry, that's not true. String theory is exactly an example of this. In fact, maybe it's worth saying that, to a lot of people who wonder why string theory is so popular, this is really the reason. At the end of the day, that's why string theory is so popular, because you think that you really are looking for a theory that is complete. Indeed, the phrase that is used is an ultraviolet complete theory, a theory that works up to arbitrarily high energy scales. And I'm even underselling the problem with gravity, because it's not just that gravity itself is non-renormalizable and gives you infinities at high energies, but the infinities depend super sensitively on not just how gravity operates, but how every other field in the world operates, because everything couples to gravity. So the naive feeling is, if you just try to come up with a quantum theory of gravity that is well defined, you need an infinite conspiracy between what the gravitational field is doing at high energies and what all the other fields are doing at high energies. It turns out string theory gives you that infinite conspiracy, because it's just one thing, a string that's vibrating in different ways, and you can show that not only are there no infinities, not only is it renormalizable, but it's finite. There's not even an infinity you have to remove in string theory. You just get a finite answer. No other approach to quantum gravity that anyone has been working on has that nice property. So as many other problems as string theory has, as long as it has that nice property, it's going to be a popular approach to quantizing gravity. The other set of problems are the conceptual problems. When we're quantizing gravity, we don't even know what it is we're quantizing, okay? Because space-time itself is on the table. One among a large number of avatars of this particular problem is what is called the problem of time. This is what we were talking about in the solo episode recently. If you naively plug away, treat general relativity like a field theory, quantize it, you get an equation called the Wheeler-DeWitt equation, which says that the wave function of the universe doesn't evolve with time. But it does evolve with time. I'm looking around, my immediate environment is evolving with time, so what's up with that? So these are conceptual problems, not just technical problems. It's not just I hit an infinity, it's just that I'm getting nonsensical answers to the questions because I don't have any firm ground to stand on. In ordinary quantum field theory, at least I have space-time. It's there, it's sitting there, it's rigid, and I know what it is, and I have some fields vibrating on it. In quantum gravity, space-time itself is part of the quantum description, and it's much harder to know where to start because that's a unique situation. There's no other versions of physics theories in which space-time itself is part of the dynamical playground. So, yeah, we don't know what time is. We don't know how Lorentz invariance involves. We don't know what it is we're supposed to be predicting. You have the wave function of the universe. Okay, what does it mean? How do you turn it into a prediction for something? No one knows the once and for all answers to any of these questions. So, yeah, gravity is special. Gravity is different as far as we can tell. Nate Wadoops says, the volume of a sphere is proportional to radius cubed, and the area of a sphere is proportional to radius squared. So it seems intuitively obvious that there are too few Planck squared units on the surface of a sphere to capture all the information contained in the much more numerous Planck cubed units of volume within the sphere. But much better informed people than me believe in the holographic principle, where something like that happens. Can you help me understand where my intuition has gone wrong here? No, I think that your intuition is completely fine. It's absolutely the case. Everyone knows that there are fewer Planck areas on the surface of a sphere than there are Planck volumes in the volume of a sphere. That's very well known. The whole point of the holographic principle is those Planck volumes in the volume of the sphere are not independent from each other, right? That's the whole point of a hologram. A real world hologram is a two-dimensional thing that if you shine light on it in the right way, you see a three-dimensional image. But the different parts of the three-dimensional image are not independent from each other. They're all derived from only 2 dimensions worth of information. So that's the whole trick in the holographic principle. You don't in holography have the ability to separately choose what is going on everywhere within the volume of space-time. Now, how does that actually play out in practice is a little bit unclear, but people are working on it. It's clearest in the ADS-CFT correspondence, but even there it's not 100% clear, so still work in progress. Sandro Stuckey says, in your January solo on the existence of time, you sketch an argument for why Boltzmann brains are not a problem once one considers quantum physics. You said that this is because thermal quantum states are static, but I could not quite follow how that solves the problem. How can the universe settle into a static state if Hilbert space is finite? Doesn't recurrence forbid that? Yeah, no, you're absolutely 100% correct. So I don't know whether maybe I mumbled through it and wasn't clear. The whole point is that this scenario where the universe settles down and asymptotes to a static state and there are no fluctuations and no Boltzmann brains, that only works if Hilbert space is infinite dimensional. Now, you have to be careful because we think that the Hilbert space of our observable universe is finite dimensional, but that's okay. Maybe there's something outside our observable universe, and maybe there's infinite more Hilbert space out there. That's what you would need to make this scenario work. We don't know if that's true or not. So if it turns out to be true that Hilbert space is truly finite dimensional, then this argument is off the table. Then indeed, you would expect recurrences, fluctuations, Boltzmann brains, all of that stuff going on. Kirsten Johnson says, do you think the holographic principle might have anything to say about why neural networks work as well as they do? I guess that depends on what you mean by the holographic principle. The holographic principle, strictly speaking, is supposed to be a statement about quantum gravity. It's not supposed to be a statement about anything else. It's not, a principle that is widely extendable to all sorts of different circumstances. It's something that becomes evident when you have quantum mechanics plus gravity, and in particular, when you have pretty strong gravity, like a horizon or something like that. When you have a black hole, when you have anti-de Sitter space, de Sitter space, a cosmological horizon, then holography becomes relevant. Even with quantum gravity, in other circumstances like the solar system, holography is completely negligible. It's completely irrelevant. You can just talk about ordinary gravity. So there's no reason why, if you don't have either gravity or quantum mechanics going on, like you don't in a neural network, the holographic principle should have anything to say about anything. Now, it's possible that there is something analogous to the holographic principle or something similar or formally comparable to it that is relevant to neural networks. That's completely possible, and I just don't know. But the neural networks that you and I know and love are firmly within the regime of classical mechanics, and gravity is very, very weak. So strictly speaking, the holographic principle isn't relevant. Marie Roscu says, when there are different types of ways to look at things, values and perspectives, can or should there be different types of democracy? Maybe, in principle, yes. I think it depends on details there. It does remind us of a really, really important fact about democracy, which is that it's hard to understand why democracy should work at all, because it revolves around people with different interests, different values and perspectives, coming together to work in a cooperative way, and sometimes saying, I didn't get my way that time, that's okay, I will live to fight again next time. And so what it means is that you're allowed to disagree about some values and perspectives, but you must share some other values and perspectives. You need to share the value of supporting democracy, right? Which I think is increasingly rare. A lot of people just would rather be governed by a cabal, a small number of people, a strongman, an oligarchy, whatever you want to call it. They think that, putting ourselves in the hands of a small number of competent people is preferable to democratic rule, and they would be able to say that quite explicitly. And so not everybody thinks that democracy is a good idea. It's conceivable to me that different kinds of people would agree on slightly different conceptions about how democracy should work, and therefore, yes, possibly, in principle, there could be different types of democracy. Some might be more direct, some might be more representative, different numbers of people might be involved, different ways of choosing the representation, and so on. Like all these could be very different, and that might be appropriate for different circumstances. Hussein says, in your last AMA, you emphasized the importance of an objective mainstream media that aspires to provide factual recounting of world events, stating that it's important for a healthy society and informed public. However, over the last 16 months, my faith in the mainstream media has significantly eroded. This is largely due to the media's coverage of the genocide in Gaza. Do you see the same disconnect between the media's coverage of Gaza, and if so, how do you reconcile this glaring disconnect between the reality on the ground and what the media has portrayed? The past 16 months have left me feeling dejected at the notion of an objective American media. Well, I think we have to first distinguish at the abstract level between two things: the importance of an objective mainstream media and then the effectiveness of the actual media we have, right? Those are two different questions. Even if you are depressed by what you consider to be the performance of those media outlets that try to be objective, that's a perfectly legitimate feeling to have. But that doesn't mean, therefore, we don't need an objective mainstream media. We need it more than ever. We need both objectivity and competence and effectiveness, right? I completely agree that the Israel and Gaza conflict, it's not the only example, but is an example of something where there are certain sort of standards and guardrails and expectations within what we think of as the objective mainstream media that prevents a lot of stories from being told. That's a problem. That's something that you should work to try to fix. We should work to try to fix. But it's not going to be solved by saying, forget about objectivity in media. Let's just have individual different media outlets that tell us what we want to hear, right? That is not actually going to solve anybody's problems. Those things should exist. That's fine, can exist. But we also need something that is common to everybody. One of the huge problems in what is going on in the United States right now is that not only are really terrible things happening at the upper level of governments, but half of the country has no idea that these terrible things are happening because they're not told by their media outlets, and that is a problem. Anonymous says, how does writing a textbook intended for a particular audience compare to writing a book intended for a broader audience? I'm curious on what challenges arise when writing those books. Is one easier than the other? It's not so much a matter of easier or harder. There's challenges in both cases. In both cases, it's super important to know your audience, right? I mean, my popular books are generally pitched at a slightly higher level than other people's popular books, because I'm not really I would like to sell, I have to say this very carefully, I would like to be the bestseller of the world. I would like to sell 1 billion copies of my books, but I am not optimizing to do that. I am not writing a book because I think it will sell the most copies. I want to write the book I want to write, and then I want people to buy it, okay? Those are two separate things. I want to write the book that is something that I can be proud of, and people who want what I have to offer will get something out of it, okay? And that's a variety of things. That might be textbooks, that might be popular books, that might be kind of in-between books like The Biggest Ideas. In terms of the challenges, for textbooks are very functional, right? They're very purposeful. It's not simply a matter of pleasure and distraction that you read them. You want to learn a skill from the textbook. I think that one of the reasons why my general relativity book has become relatively popular is because there's a lot of general relativity books on the market. Many of them, I'm trying to say this very politely, they're not meant to teach people general relativity, or at least they're not trying as hard as they could to teach people general relativity. They're trying to get it right, to sort of put forward some body of knowledge that the author thinks is important. But when you write a textbook, you have to take into account who's reading it, where they're coming from, what they already know, et cetera, et cetera. And there might be things that you think are really cool, but putting them in your textbook isn't actually helpful to the audience members. So optimizing for actually teaching the subject is the very simple strategy that I had in mind. For the quantum mechanics textbook that I'm working on very, very slowly, but is still going on, it's a slightly different thing. Again, there's many, many quantum mechanics textbooks on the market, and some of them do actually try their best to be optimized for pedagogy. But I think there, the subject matter is the issue. For general relativity, everyone more or less agrees on the subject matter. For quantum mechanics, and this has nothing to do with, interpretations or many worlds or anything like that, the actual quantum mechanics, the actual thing you're supposed to teach, so undergraduates are empowered to go solve problems and, solve equations and so forth, people disagree on what that is. How important is it to talk about entanglement, or how important is it to talk about measurement? How important is it to talk about two-state systems or quantum information rather than just solving the Schrodinger equation over and over again for different explicit potentials and things like that? People disagree about these things. And so I'm going to try to I have a strategy. We're going to see how it works. I'm teaching it, which is always very, very helpful. So it's really a matter of effectiveness in a very, very tangible way. So the difficulty of writing a textbook is just being as clear and useful as possible. The usefulness is something that I would emphasize there. For a popular book, there's a lot more freedom, right? The objective of doing it is much less predefined. You can write books for inspiration, for education, to be thought-provoking, to synthesize a whole bunch of different things. There's all sorts of different reasons why you write a popular book. But you still have the challenge of trying to match what you think is cool and interesting with what the audience might be interested in. Obviously, for the popular book, you don't need to worry about getting all those equations right. But for the textbook where you do have all those equations, the thing is that the equations are either right or wrong, right? You can actually test them as kind of tedious. You better check, when you have problem sets or things like that you suggest in your book, you better check that they're doable and they're sensible and all your derivations are correct and you're free of typos. All that stuff becomes very, very relevant, less so in a popular book. But in a popular book, you really should think carefully about, why am I saying this at all? Why do I have a chapter on this? Is this really necessary? Could I do it better? Could I talk about something completely different? Just because it is so much less constrained, it can be trickier to choose how to do it well. Ved Kumar says, priority question. I recently finished your Biggest Ideas in the Universe series and have found it helpful in my understanding of foundational physics. It prompted a thought on the quantum measurement problem I wanted your feedback on. The idea involves trying to entangle a superposition into a classical and quantum system while requiring information conservation and considering the implications. A useful case of this is trying to pass a data sequence, which will be a superposition of several definite sequences all equal in length, onto a classical and quantum computer. Both computers will contain bits and qubits equal in quantity to the length of a definite sequence. So the question goes on. I'm going to stop reading there, but I do not understand what is going on in this question. I know it's a priority question, so I have to address it, but I am not at all clear about the setup that is being proposed to be judged. When you say entangle a superposition into a classical and quantum system, that makes no sense to me. I mean, I'm sure it could make sense if I understood what you had in mind. Maybe there's some equations or something like that, but entanglement is a purely quantum thing. There's no such thing as entangle a superposition. I don't even know what entangle a superposition means. I know what it means to entangle quantum states, and quantum states are in superpositions from certain points of view, not in superpositions from other points of view. But classical systems are neither entangled nor in superposition, so I really don't know what's going on. Sorry about that. I can't really be very helpful. Stephen Moradi has a priority question. I like everyone's using up their priority questions. That's good. You put some thought into what you want these to be. I've heard people say that there is no chaos in quantum processes. Could you elucidate the difference between a three-body classical gravitational interaction with a three-body electrostatic quantum interaction, given that both are deterministic and interact via inverse square forces? This is a subtle thing, this statement that there is no chaos in quantum processes. I mean, the world is quantum, and there is chaos in the world. So therefore, clearly, in some sense, there is chaos in quantum mechanics. But on the other hand, chaos is a statement about sensitive dependence on initial conditions, right? Tiny deviations in the initial conditions lead to large deviations in the final answer. How can that happen? At the down and dirty level of equations, it happens because of nonlinearities, because small deviations in the state of the system can feed back onto each other through nonlinear terms in the equations of motion. In quantum mechanics, the equation of motion is, you guessed it, the Schrödinger equation. And the Schrödinger equation is resolutely linear as a function of the wave function. There's no wave function squared terms in the Schrödinger equation. So if the question you're asking is there sensitive dependence on initial conditions in the evolution of the quantum state according to the Schrödinger equation, the answer is no. There never is. It's a linear equation of motion. But within all of the different things that can pop out of the Schrödinger equation, one of the things is the classical limit. So you can have a classical limit, and it makes absolutely no difference whether we're talking about gravity or electromagnetism. They're exactly the same in this sense. In either case, there can be a classical limit where there is chaos, where there is nonlinear classical equations of motion that arise as the limit of quantum mechanics. How can nonlinear equations of motion arise as the limit of linear equations of motion? Well, the classical limit is subtle, and it involves the combined effect of many, many different parts of the quantum mechanical wave function. So basically, you have many, many different modes, or whatever you want to call them, of the wave function, either interfering constructively or destructively to give you a classical trajectory. And that emergent classical trajectory can indeed obey chaotic dynamics. The whole thing is very subtle. I'm not trying to undersell it. There was a whole subject for a while where people were trying to bang their heads against this question. How can there be quantum chaos? And the answer is you need to take the classical limit. Paul Turek says, on the memory arrow of time and the causal arrow, you said, because we have memories and records of the past, we can't change them. But I'm tempted to turn the explanation around. If you can, at time t1, select an event, so you can't, at t1, have a record of the event. I inserted a word there. If you can, at time t1, select an event, you can't, at time t1, have a record of the event. So it seems that either lack of influence is a precondition or else a co-condition of records. In Janan Ismail's book, How Physics Makes Us Free, she offers a united explanation of both arrows of time, influence, and records. Local macroscopic changes to the present state of the world propagate asymmetrically into the past and future. So who's right about the direction of explanations here? Or is this a case where, depending on what the audience already understands, the explanation can go either way? I do think there's a unified explanation here, and I might have been, or the specific language that I used might have been chosen sloppily here. When I say because we have memories of records of the past, we can't change them, what I mean is because we have what we think of as reliable memories and records of the past, we know we can't change them. But our knowledge of the fact that we can't change them is different than the fact we can't change them. I don't love the language of macroscopic changes to the present state of the world propagating asymmetrically into the past and the future. I'm not quite sure what it means that they propagate. But of course, you can invent a meaning for it. I'm not saying that it's meaningless, but I'm saying that you have to be very clear. There's more words that would need to be stated to go into what exactly is being said. But anyway, I don't think there's any weirdness or mysteriousness or true disagreement here. The overall unmistakable fact is you have some macroscopic incomplete information about the present. You have some hypothetical information about the past in the form of a low entropy boundary condition. You have no information about the future. There's no boundary condition that you are imposing there. And given those three ingredients, you will get an asymmetry both of memory and causality. Ryan Hibbs says, the light we see from stars represents the object as it was in the past due to the speed of light, and the further away the object is, the faster it's moving away from us. How do we know from just this data that expansion is accelerating, and not that expansion just used to be faster in the past than it is in the present? cosmologists aren't dummies, okay? They have ways of thinking about this. They know what the issues are. And the thing is, you don't simply, these words that we use when we talk about these in ordinary language don't map exactly onto what real cosmologists actually do. The point is that cosmologists have a model. They don't just use words like, the universe is expanding, the universe is accelerating. You say, I have Einstein's equation in general relativity. Under assumptions of homogeneity and isotropy, this turns into a differential equation for the scale factor of the universe, the relative size of the universe at different times, called the Friedmann equation. And the Friedmann equation depends on the sources of matter and energy and curvature in the universe, the amount of ordinary matter, dark matter, radiation, vacuum energy, etc. And with all of these ingredients, the specification of what those ingredients are, how much matter, how much radiation, et cetera, at any one moment of time, allows you to predict what the observed relationship should be between a redshift and a distance. And then you match the data to the observations, and you figure out, the data will match the observations if 70% of the universe is dark energy, vacuum energy, 30% is matter, and 10 to the minus 4 is radiation, something like that. Now, when we explain this to people, they don't want to hear that. They want to hear the universe is accelerating or the universe is not accelerating. And that's true. Those are accurate statements. The universe is accelerating right now. But the way that you actually get there is this very careful procedure of matching data with theoretical predictions. Ken Wolf says, I recall you saying that you are not fond of the old-fashioned cocktail because it depends too much on sweetness for its flavor. Is there any whiskey or scotch-based cocktail that you do like, or is anything more than a splash of water simply not acceptable? Well, look, everything's acceptable. I hope I've been clear about that. You can do whatever you like. I have my own preferences. If you include American whiskeys like bourbon and rye, then certainly I love lots of cocktails with whiskeys. I'm a huge fan of Manhattans, among other things. I don't know exactly what the definition of whiskey is as opposed to other spirits. So I don't know, is brandy whiskey, is cognac whiskey? I think typically not, but they're comparable. They're similar in certain ways to bourbon or rye. Scotch is notoriously a spirit that is hard to turn into cocktails, right? It's so unique and it's so flavorful on its own that either drinking it neat or over an ice cube is how I would generally go. Kelly Hoogland says, what do you think the average person misunderstands the most about artificial intelligence and large language models? For me, I've heard a lot of buzz about how ChatGPT is much more water and energy intensive than a standard Google search, a fact which people are now using as a moral argument against people using it at the individual level. I feel like this completely misses the mark and is analogous to shaming someone for forgetting to bring their own grocery bag and turning a blind eye to corporations' profit-maximizing behavior. In my opinion, this is a greater misunderstanding than the fear that AGI is going to take over and start ruling us. Maybe that's possible, but plenty of people do shame each other for not bringing their own grocery bags. This is just a feature of human nature. It's not a great feature of human nature. I'm on your side about deploring it, but when we see individual behavior, we find that very judgeable in a way that the invisible corporate or systemic, or government for that matter, behavior behind the scenes tends to be a little bit more invisible. Going back to the shooting the United CEO kind of thing, right? I mean, how do you compare the crime of shooting an individual person on the street to the crime of denying a whole bunch of people health care, right? One is much more visceral and visible. In the case of AIs and large language models, I do think that there is some tribalism going on, some choosing of sides, because there's a whole bunch of reasons why you might be either skeptical or outright hostile to AIs. One reason is the way that they have been deployed by corporations, right? Google searches or Microsoft products are now full of AI when nobody asked for it. Another reason is if you're an artist or a writer, or for that matter, any other number of professions that have their livelihoods in danger of being stolen away by AI. Or that, like you say, there's the worry about resource usage in various ways. And these are very different objections, right? Like these are not the same objection, but we get aligned. We care about one of these objections and we start relying on other ones just to build our case because we've already decided what side we're on, and then we just collect evidence to make our side happy. I think that the question of using up resources is a very tricky one. I mean, it is clear that as a whole, on the aggregate, AI and other, the label AI is a little not exactly appropriate here. People are using computing power for all sorts of things, but computing power broadly construed uses up an enormous amount of resources, uses up an enormous amount of electricity and water and things like that. I've seen plenty of people complain about this. I have not seen much of a sensible breakdown of how much an individual attempt to make query ChatGPT about what is the best way to make a noodle dish with ground pork or something like that. Does that really use up an enormous amount of electricity compared to something else? I honestly don't know. I'm saying that I haven't seen it carefully compared to other things that we do. Right? People, this is just, again, another very basic human flaw. We like to think about total amounts rather than rates, but the rate is what matters. What is the rate of an individual person's use of AI in terms of electricity and water consumption versus other uses of AI? People in California work very hard to not run their faucets too much because there's a water shortage. But the enormous fraction of water is used by agriculture, not by people running their faucets. That's not to say that people should waste water running their faucets, but it's just very hard to get accurate information about the actual scope of the problem versus the thing that you feel you personally can have a handle over. I think that the real danger of AI is neither one of these things, is neither power usage or AGI taking over and ruling us. It's that we start handing over really crucial functions of society and technology to algorithms we don't perfectly well understand. And that is going to lead to very down-to-earth, mundane failure modes that I can foresee happening in the future. So I think that there are very legitimate worries about this technology, but they don't always match up to the worries that people spend a lot of time talking about. Rue Phillips says, did Google's quantum chip Willow really tell us anything about the multiverse? Is there any measurable connection between quantum computing and many worlds? I should have grouped this clearly with the earlier question, so no. There's no measurable connection between quantum computing and many worlds. There is arguably a connection between quantum computing and wave function realism. I think someone like David Deutsch would say that, in fact, he has said, I don't need to think it, he has said that hidden variable theories, which are also wave function realist theories, and also say that the wave function strictly and only obeys the Schrodinger equation, Deutsch would say these are just Everett in disguise because you have the whole wave function. It's going to branch. It obeys the Schrodinger equation. There's going to be decoherence. All of those things are true. And he would say that the advocates of pilot wave theories then add these hidden variables and say, okay, yes, but this is what's real. And he just doesn't believe that that makes any sense. So I don't really think that anyone who advocates any currently popular interpretation or foundational approach to quantum mechanics would be surprised that quantum computers work. And therefore, to be fair, I don't think that we have gained any information that changes our credences about these different approaches. Anonymous says, have you considered doing 23andMe or similar services? You've mentioned that you don't know much about your ancestry. Could be interesting to learn. Maybe there's a physicist somewhere in there. It also provides a lot of useful medical info. So no, I have not really. I'm not that curious about my ancestry, and I'm very worried about handing over my genetic information to faceless corporations. I mean, in fact, it became clear that 23andMe in particular had worked out quite an amazing gimmick because they are taking all of this data from people who have handed over their data to them, and they're using it to do pharmacological experiments and things like that. They're basically, ordinarily, the corporation would have to pay the person to get the data that they needed. But 23andMe figured out a way that the people paid them for the privilege of giving them their data. I don't think that was a very good bargain. Of course, genetic tests can provide a lot of useful medical info, but if I ever thought that that was something I needed to do, I would just try to do it on an individual level with a doctor, not with a corporation like 23andMe. Not that it's bad to have done it, but that's the bargain that I would personally make. Ilya Lvov says, thank you for your solo episode on emergence. In it, you provided the definition of emergence as the operations micro theory goes to macro theory and time zero goes to time one commuting with each other. Doesn't this by definition rule out strong type 3 emergence? Isn't the point of the strong emergence that the macro theory predicts brand new outcomes, and that the micro theory starts being wrong at a certain scale? Yes, that is completely true. So if you think that strong emergence can happen, then that simple idea of the commuting diagram between time and the emergence map would fail. And in the paper, we say that very explicitly. I still think it is useful to start with that conception because it's easy to understand. I know that out there in emergence land, or in the land of people who talk about emergence, there is a strong constituency that resists any version of emergence that is understandable. They think that emergence is only an interesting concept in those cases where you can't understand what's going on. And I resist that. I don't think that's true. In some cases, you can certainly understand what's going on, and they would say, therefore, that's not emergence. I would say it's a kind of emergence. Let's understand this first, and then let's add on the weird stuff that you want to add for the strong emergence later. Right? That's my personal preference. Nicholas Sharosky says, given your stance on poetic naturalism and emergence, would you say that when describing a sunset, both person A, who says shorter blue and violet wavelengths are scattered by Rayleigh scattering, and person B, who says the light dances, transforming the sky into a fiery canvas, are using sufficiently accurate and useful vocabularies to be considered real? How does this align with your notion of emergence, where different levels of reality and their descriptions must remain compatible? Does the poetic vocabulary of person B, in your view, fall short of the scientific one of person A in capturing reality, or is it equally valid? I don't think it's equally valid. I think they're both completely valid, right? But that doesn't mean equal, you know? They're trying to do different things. If I said, could you explain physically why the sunset looks more red than blue, and someone gave me the answer, the light dances transforming the sky into a fiery canvas, I would not give them full credit on an exam, okay? Likewise, if I said, give me a poetic description of the feelings that this sunset evokes in you, if you started talking about Rayleigh scattering, I would not give you a full marks on that exam either. I think it's relative to the kind of thing you're trying to achieve. Now, there's the additional factor that in these two cases, the kinds of things you're trying to achieve, a scientific understanding of photon scattering versus a poetic description of the feelings that are invoked by the sunset, have different standards of success, right? The scientific kind of description there is much more precise and rigorous and testable and quantifiable. And the more poetic description is a little bit harder to judge whether it's successful or not. That doesn't stop them from both being accurate or both being real. They're just trying to do two different things. Nico Bersianic says, my question is about quantum field theory. When an observer travels in space, for example, do they cross quantum fields? Is there a way to verify, to measure that we're traversing through all or some quantum fields by moving, or on the contrary, fields are always anchored to the observer? Certainly in the way that we think about quantum field theory and what quantum field theory means, the fields exist everywhere. That's what it means to be a field. A field is the answer to a question at this point in space, what is the value of the field? For every single point in space, a field has a value. The electric field has a value at every point in space. It might be zero, so you might say there's no electric field here, but you don't actually mean the electric field doesn't exist there. What you mean is the value of the electric field is zero there. Just like when you have a function of y as a function of x, if that function happens to cross through y equals 0, you don't say the function stops existing, you just say that its value is 0. If the temperature is 0 degrees Fahrenheit, you don't say there's no temperature, you just say the value is 0. Same thing with quantum fields. They exist everywhere. They're not pulled along or traveling along. You absolutely do pass through them in the sense that you pass through space, and the fields are everywhere in space. I don't know how to pronounce this. Ptmilo, Ptmilo, Private Milo maybe, says, is your objection to the potential for large language models to exhibit more generalized and extrapolation-heavy intelligence based on deeper principles, or is it more intuitive? That is there anything in information theory that tells us it is impossible for locally generated interpolations of tokens to uncover patterns and sequences that are indecipherable from conventional human-like extrapolation successes? Well, I don't think it's based on deeper principles in the sense that there's a proof that you're asking about. In fact, I'm open to the possibility that large language models could construct. Let's back up. The large language model is optimized to give sensible sounding answers to human beings asking questions of it, okay? Now, it may very well turn out that in that black box of many, many layers of deep learning, the way the LLM does that is essentially to invent intelligence, to invent a model of the world, invent sort of counterfactual reasoning, invent all those things. I'm open to that possibility. However, number one, I don't see why that would necessarily be the case, because that's not how you've programmed the LLM. It would have to be a case where the optimization procedure was just so successful that the LLM found it itself, despite the fact that that's not what it was trained to do. And number two, in the data, I see no evidence of that happening, right? It's not that LLMs don't become better and better. They're clearly becoming better and better, but they aren't perfect, and they make mistakes and they make failures. And my point has always been the types of failures they make are precisely the type you would expect if they were not being real human intelligence, if they were not causally mapping the world and inventing counterfactual reasoning. So I am very open to new evidence coming in that changes my mind. That would be super duper interesting if it were true. I just haven't seen it yet. Ed says, I know you're not an AI expert, but you have had a number of AI expert guests, so you likely have a better handle on it than I do. Do you have a sense as to whether there's a fundamental difference between the theory of operation of an AI LLM and that of an autocorrect feature on my phone? Is it just a massively scaled up version of this thing that is always failing to guess the next word I want, or is it doing the same thing in some utterly different way? I think it's both. It's a little bit half and half there. Certainly, there's a spiritual connection between LLMs and autocorrect. Autocorrect is not a separate kind of technology, right? Autocorrect is next token prediction. And in a very real sense, LLMs are very, very, very souped up next token prediction. It's not just the next token. They're predicting more than that. They have some memory of what they've been talking about and things like that. They have very important, crucial distinctions between a simple autocorrect kind of thing. But there is that spiritual connection. So I think that there's both a similarity and a difference there. Jesse Rimler says, I'm currently reading the wonderful new David Bentley Hart book, All Things Are Full of Gods. It's a thoughtful and engaging philosophical treatise on consciousness and materialism written as a Platonic dialogue. Hart is religious, and I generally disagree with him. I'm guessing you would too. But it does make me think about the areas where non-materialists can find argumentative purchase. Do you think that the irreducible experience of consciousness is one of those brute facts that allows otherwise rational thinkers the wiggle room to play around with non-scientific ideas? If I understand what you're asking, no, I do not think that. I'm not sure what the word irreducible means in the phrase the irreducible experience of consciousness. There is an experience of consciousness. How do I know it's not reducible? I don't even know necessarily what reducible means. I worry that it means different things to different people. I've been very, very clear about what I think consciousness is. I think that people obey the laws of physics, and I think that we talk about people using a higher level emergent vocabulary, which absolutely includes all the interior first-person consciousness talk. I don't think that there's any fundamental difference between that and the exterior talk that we use about how people are moving or talking or thinking or whatever. So I think that there is some temptation to treat consciousness as different precisely because it is first person. There is something unique about my consciousness from my perspective, sure, but I want to understand the world comprehensively and fundamentally. And I think that by far the leading way to do that is to not treat me as all that special, including my consciousness. It's just a higher level emergent way of talking about the collective behavior of atoms and electrons and photons in my brain. Polina Vino says, computable analysis is a kind of analysis that is compatible with computability theory. For example, we have the computable intermediate value theorem, the assertion that if f is a computable continuous function and f of a less than c less than f of b for computable reals a, b, and c, then there's a computable d with f of d equals c. I think does that make sense? You have a function, and you know that the function at some argument is less than c, and that is less than the function for b. Then in between, it had to go through c. That does make some intuitive sense. The idea is that these computable theorems do not say anything about numbers that cannot be expressed in terms of an algorithm. Do you think that this type of analysis has any place in physics research, such as in the effort to make relativity and quantum mechanics compatible? For example, maybe limiting mathematical results used in computations to only those that discuss computable functions and values could expose where we helped ourselves to conclusions about things we can't even express. Well, it's possible. It's absolutely possible, but I don't see how exactly that could happen. For one thing, let's be clear. Relativity, in the sense of special relativity, Einstein in 1905, is 100% compatible with quantum mechanics. That's where quantum field theory comes from. General relativity, which is Einstein's theory of gravity, has not yet been quantized. Or, to put it slightly more carefully, we do not yet have a quantum mechanical theory that in the classical limit achieves all of the predictions that general relativity does. Okay? But that's still a problem. You're suggesting that a particular kind of focus on a particular subset of math might be helpful, computable analysis. It might be. That's just too vague of a suggestion to me to really think about. It's like, there's a lot of cool math out there, right? Category theory is something that is very exciting among mathematicians right now. We talked about it with Emily Reel on the podcast some time back. And a lot of people are very optimistic that this is going to help us understand some deep questions of physics. The proof of the pudding is in the tasting. It's great to be excited by cool math, but you can't just say, I think maybe this is going to help solve some problems. You got to solve the problems. I'm sorry, that's just how it works. In order to get people excited, you have to kind of show them the money. You have to give them the killer app. Schleier says, your discussion with Stone Farmer touched on the fact that our economic system averages growth of around 2 or 3% per year, which I believe means a doubling in size every few decades. It's surprising to me that there isn't more work being done to come up with an economic system that can thrive and persist but not grow. Why don't we inevitably need that given finite resources? Do you have thoughts on why this isn't a significant focus of economists or others who study complex systems? Well, I do think that this kind of thing is a focus. If you mean how could we make a transition to a fixed economy rather than a growing one, that's not much of a focus of economists, because I don't think that most economists think it's either plausible or desirable. For one thing, at the very, very most basic level, the population of the Earth is growing, right? So there are more people. If you had an economy that didn't grow, that would be less and less resources per person, and no one's going to vote for that. But even if you do live in a country where the population is not noticeably growing, people like to think that their descendants might be better off than they are, right? That is something that is very much a goal of a lot of people. I think at a down-to-earth level, there are reasons why growth and indeed a little amount of inflation are useful. Just to give you one very, very easy to understand one, it is helpful if I want to different things. Maybe I want to buy a house, but maybe I also want to start a company, right? For various reasons, I might want to take out a loan. That is borrowing so that I have money right now against the promise of a future payment. A tiny bit of inflation will ease the burden of paying back that loan in the future, and therefore make me more likely to take out the loan, and therefore in a well-functioning economy makes it a little bit easier to make progress and have everything be active and churning and new things going on. Now, of course, this is a tricky thing because you don't want too much inflation. That means that everyone's savings disappears. So there's a very, very fine line to be drawn there. And of course, getting it right is what economists talk about all the time. I do think that it's just wrong to think that, things would be easier if we fixed everything at a constant value of GDP and just tried to keep it completely stable like that. It's hard to make it stable. For one thing, there are fluctuations up and down. So if the overall trend is growing, then the downward fluctuation is relatively benign. Whereas if the overall trend is flat, then a downward fluctuation can be pretty devastating. So maybe there are good reasons why you don't want that, and maybe that's why it's not a significant focus. Zach McKinney says, inspired by your episode with Addie Pross, if you were to consider and model functional democracy as a dynamic, kinetically stable system, then what are the inputs or conditions that you would hypothesize are needed to maintain kinetic stability? So I'm answering this question because I have no idea what the answer is, but I think it's a super important question in some version or another. So I don't understand the specific idea of dynamic kinetic stability well enough to say that that's the right kind of model to use. I mean, it's a little bit specific to chemistry, honestly. But the more general idea, if you remove the word kinetic and just say, dynamic stability, that's a very general idea. Lots of things are sort of stable in the aggregate, stable at a macro level, like a human being is certainly mostly stable, right? Like I don't change my configuration dramatically from moment to moment, but only because I take in fuel from the outside and then throw away entropy and energy back to the world. The biosphere as a whole does that. Waterfalls, the great red spot on Jupiter, many different things. So you want a functioning democracy or any kind of functioning country for that matter to be something like that, right? I mean, the individual human beings are allowed to move, but the overall shape of the country maintains some coherence. And you also want it to be stable. So, I mean, just like the economics question above, you want perturbations to fluctuate rather than to grow, right? Stable to a physicist means if I poke it, there's a system that I poke, so I do a little perturbation, I change something about it. Does the perturbation sort of oscillate back and forth, or does it grow bigger and bigger? If it grows bigger and bigger, then it's unstable, and that's bad. So that's a positive feedback loop, right? When a tiny deviation in one direction keeps growing in that direction. Doan Farmer's point is that it is often in the economy very typical to have these unstable positive feedback loops, and the complexity economics perspective is supposed to help with that. I think there's been much less study about that at any quantitative level for political science, for democracy. There's been a lot of sort of qualitative political science and historical work on the stability of democracies or the lack of stability sometimes. But thinking about it in terms of physics systems or chemistry systems has not been done a lot. I would like to see more of that. I'm going to do more of it myself, and I'll let you know if I come up with anything good. Haven't quite yet. Tim Giannitsos says, a great hits and misses episode. You mentioned that your paper about the origins of the arrow of time avoids making an assumption about a single low entropy beginning. But does it just make a different assumption that the natural state of the universe is empty de Sitter space? So two things. Number one, no, it does not make that assumption. It says we make an argument, a very hand-wavy argument, to be sure, but the argument is if you're not in empty de Sitter space, you approach it. It's basically the cosmic no-hair theorem proven by Bob Wald back in the 1980s. And then there's a reason for that. The reason for that is that in the presence of a positive cosmological constant, de Sitter space is the highest entropy state. So that's the whole point, part of the whole point of our paper, which is that you have to start somewhere. By start, you don't mean the initial condition of the universe, but you have to have a condition for the universe at some moment of time, and then you try to evolve it both forward and backward. And our point was, you don't have to tune that condition at all. It can be very, very natural, very, very generic. And you can think of that as either saying, well, I'm going to pick the most generic state, and it would indeed be empty de Sitter space. Or you can think about saying, I want to allow for other things, but guess what? Those other things evolve into de Sitter space. You get the same answer either way. Eric Haugen says, in the solo episode about time, you talked about stuff fluctuating into existence, maybe even the universe itself. It isn't clear to me what you imagine that such a universe-producing fluctuation would look like. Would a super dense expanding bang instantaneously appear from nothing? Or would white holes grow from radiation and spit out stars? Would the dead rise from the ground and ungrow into babies? Would galaxies dissolve into smooth gas clouds just in time for the big crunch, just by chance? If it was time symmetrical, would it even make sense to call one of the two histories a fluctuation? So I'm not sure exactly what you're referring to. This is entirely my fault about the stuff fluctuating into existence. For the universes fluctuating into existence, if I said something like that, I did not mean the entire universe fluctuating into existence. That is not something that I particularly have contemplated. I don't even know what that means. If there was no universe, what is there to do fluctuating? We did have in this scenario I was just talking about, the one from the Arrow of Time paper with Jennifer Chen, we had the idea of baby universes, where you have a pre-existing universe that can undergo a fluctuation inside itself that would cause a little tiny bit of universe to pinch off and go its own way. There we have a picture of what it would look like. It would look like, well, let me emphasize the important point here. The amount of baby universe you need to pinch off is very, very tiny. It's just a little Planck scale sized thing. You don't need to undergo the entire history of the universe backwards. It's not anything like that at all. What it would look like is a number of particles, photons or whatever. I'm not sure what the most likely thing would actually be, but a bunch of particles come in by random fluctuation and collide with each other in a small region of space, enough to make what looks to the outside like a black hole, but actually inside is a baby universe pinching off. And then that thing that looks like a black hole then radiates away, and that whole process looks more or less symmetric, right? A bunch of particles come together, make a black hole evaporates into a bunch of particles. But the set of particles there is enormously smaller than what you would need to make a big universe-sized thing like us. The reason why that's viable is because of inflation. Because inside the baby universe, you can use the laws of physics, take advantage of the property that a closed universe has zero total energy. So if that closed universe is full of an inflaton field, it can expand to an arbitrary size, and that inflaton field can turn into ordinary matter and radiation and create many, 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 many more particles than you actually needed to make the baby universe in the first place. If what you're referring to is some self-contained universe, then I would not use the vocabulary of fluctuating into existence. For a baby universe that comes from a pre-existing space-time, I think that language is appropriate. For the universe as a whole, if you mean a universe that just has a beginning, then I would just say it's a universe that has a beginning. I would not say that it's fluctuating into existence out of nothingness or anything like that. Johann Yartelius says, can a molecule be earmarked? There's this factoid, or perhaps truoid, that with every breath we breathe, we get an oxygen atom once breathed by Julius Caesar. Now, from a probability point of view, I'm sure this makes mathematical sense. But if one would want to test it, how would one do so? Is the likelihood larger that a water molecule, for instance, stays closer to where it met me, or is the dispersion equal? If I wanted to register individual molecules to see if that particular molecule returns to some given point, i.e. a water molecule passing through my faucet again, could I do so, and if so, how? So to the actual question, can you earmark the molecule? Not really is the answer. It depends on what you mean. You can always take that molecule and attach it to another molecule. But if you're talking about an oxygen atom or a water molecule, they're sufficiently small that if you attach them to large other molecules, you're going to completely change their dynamics, right? They might not even float in the air anymore. But individual molecules is an interesting physics point. Let's start with an individual atom. An individual oxygen atom, oxygen atoms can be in different states, but by different states, what we mean is the electrons in those oxygen atoms can have different energy levels, okay? As we talked about earlier, when you're in a higher energy level for an electron in an atom, you tend to relax, you tend to decay down to the lowest allowed energy level. And so typically, oxygen atoms are going to be in their lowest allowed energy levels. And all oxygen atoms that are in the same lowest energy level are indistinguishable from each other. They are literally indistinguishable particles in the quantum field theory sense of the term. So there's no marker. There's no way to say this is this oxygen molecule, that one is that oxygen molecule, or atom, I should say. But even as you get to molecules, molecules are more complicated, they have more moving parts, so it becomes slightly easier for more things to happen. Molecules can vibrate and stuff like that. But if we're talking about things as simple as a water molecule, there's not an interesting set of vibrations that it can have, and even those vibrations decay away, so they all look alike. So no, you cannot really watermark the molecules. It's true that if Julius Caesar breathes a breath, the atoms that he's just breathed out will, for the moment, mostly be near him. They're not going to instantaneously spread through the universe or spread even through the Earth's atmosphere, right? So when people make these statements, they are absolutely not just using numerology about how many atoms there are. They need to make statements about how quickly the Earth's atmosphere mixes, how quickly a test particle, if I have one particle in the air that is floating randomly, well, you know what the temperature of the air is, you know what the typical velocity is, and it's doing a random walk, it's bumping into other molecules. So you can ask the question, how long does it take to sort of randomly go throughout the whole Earth's atmosphere? And the answer is less than 2,000 years. So that's why there is some quantitative sensibility to that kind of statement, even if you can't actually look at the individual molecules. DMI says, is the feeling that only the present we see is real, even though nothing in the physics equations makes it more fundamental than any other slice of space-time, could that be the same kind of illusion that gives us the feeling that only the branch of the wave function we see is real, even though nothing in Schrödinger's equation makes it more fundamental than any other branch? Kind of, I guess. I like the analogy, and I'm trying to decide whether or not I think it's a completely accurate analogy or not. The wave function case is actually easier in this particular example because even though the wave function itself is very abstract, it is indisputable that if you believe any of the usual Everettian story, any individual agent is located on one and only one branch of the wave function, and that's the branch they see, and that's the branch they naturally attribute reality to. And that's true across time, right? Not just for a moment, but in future moments as well. Whereas for the presentism question, you have to say, well, you have to distinguish between the agent at one moment and the agent at another moment, right? At any individual moment, the agent only sees a little bit of their immediate environment, but they attribute reality in the casual presentist kind of way of doing it to a whole slice of the universe very far away from what they see. So there's my worry about saying it's a perfectly good analogy is that there is more extrapolation in the presentism case, right? It's more model dependent. It is more relying on the fact that I'm not only considering what I see around me right now, but I'm also treating everything at this one moment of time as equally real. And of course, everyone knows that relativity is a huge challenge to presentism because different people moving at different velocities would extend their present moment of time differently. So how in the world can it be true that only one slice is real? Of course, the sophisticated presentists have answers to that. Since I'm not a presentist, I've never put any work into understanding what those answers are. Joan Baluda says, priority question. If you could get the definitive true answer to any open-ended question, what would that question be? The answer would be complete and thorough in a scientific paper. Yeah, it's a boring answer, but I guess I would say, what is the correct theory of everything? You know, what is the correct theory of gravity and space and time and all the forces and quantum mechanics and all that? Just tell that to me. I think that hopefully a scientific paper would be long enough to explain it in language I can understand. I don't know. I'm not expecting anyone to give me that paper anytime soon, but, that would be pretty awesome if it happened. Alexander Carroll says, is there a theoretical mechanism how, when time emerges separately from space, the whole of space-time still ends up exhibiting this high degree of symmetry, basically Lorentz invariance or diffeomorphism invariance, all these different ways in which relativity convinces us, this is me, Sean, talking now, not Alexander, all the different ways that relativity teaches us that space and time are unified into space-time. How does that come out of this? And then Alexander continues, naively, I would expect that an emergent time parameter would not magically fall in place to form a nice representation of these exact symmetries with the rest of space-time, and all the fields being in representation of these as well, but instead stick out like a sore thumb. So I think it's a very good question, a very, very important question. We don't know how this is supposed to work. So I think that there's two kind of competing intuitions going on here. One is, if I started with a theory in which time and space were clearly different, I just told you what was going on in space and separately had an equation telling you how things evolve in time, why in the world would that knit together? So you build up by evolving in time, here's space at a moment later, here's space a moment later. And by space, I mean not just space itself, but everything in space, the whole configuration of the universe. And I build up a bunch of these, okay? And then I say, okay, I've knitted together a four-dimensional space-time. Is it true that we have these symmetries like Lorentz invariance that we know and love from relativity? From that perspective, I agree. It would seem weird, right? That you would just magically have this invariance where I could now completely switch to a different perspective and slice space-time differently and get just as good, the same laws of physics, basically. But there's another intuition, which is, let's say that I have a theory that does have this invariance, that is Lorentz invariant, that does have the symmetries of relativity built into it. I am 100% allowed to pick a reference frame, to pick a decomposition of space-time into space and time, to, within the terms of that decomposition, describe what's going on in space and write down equations telling me how it evolves in time. And so there's no obstacle to building entirely symmetric descriptions in a language that is manifestly not symmetric. And so we're asking the question, under what conditions does this step-by-step, moment-by-moment building up lead us to something that shares all the symmetries of relativity? And the answer is, I don't know. I mean, there's something very nice about the symmetries of relativity. So I'm not in any sense convinced that they couldn't come out generically under some scheme, but I don't actually know. I know, and people have tried, by the way. At least I am aware of the existence of various papers about the emergence of Lorentz invariance from not obviously Lorentz invariant descriptions. Diffeomorphism invariance is a very different thing. That's almost automatic. That's basically coordinate invariance. It's hard to not be diffeomorphism invariant. Or let me put it this way. Diffeomorphism invariance, which for those of you who don't know, is basically coordinate invariance. It's basically saying I can choose whatever coordinates I want, but there's sort of an active and a passive version of that. Changing the coordinates and leaving the underlying system invariant is one way of saying it, but then keeping the coordinates and moving the system is another way of saying it. That kind of sounds more impressive. But in my mind, diffeomorphism invariance is a real thing, but it's a real thing that is a label that gets attached to descriptions of theories, not to theories. So I can describe Newtonian gravity in a 100% diffeomorphism invariant way. I don't, because it's just more convenient to treat space and time differently, explicitly, to pick coordinates on time and coordinates on space separately, but I don't have to do that because it's a description statement, not a theory statement. Whereas Lorentz invariance is a theory statement. Some theories are Lorentz invariant and some are not, so I would treat those differently. Anyway, yes, I would love to know whether or not Lorentz invariance under some very simple assumptions naturally emerges, and I don't know the answer to that one. Brendan Hall says, I've convinced myself recently that TV and subsequent technologies for passive entertainment have worsened the quality of our lives by making leisure more isolated from our fellow people. To what extent would you agree with this sentiment? I get it. I think that you're correct that leisure is now more isolated from our fellow people. Arguably, computers have done that, and smartphones even more than TV has. On the other hand, it's given us a whole bunch of enjoyment and entertainment that we didn't used to have. How do I weigh those two things against each other? I truly don't know. My own feeling is that probably TV is a net good. I don't really want to go back 200 years to a place where I have to learn to play the piano and sing to get my entertainment in the evening, but I have no objective way of actually doing that comparison. Nikola Ivanov says, it seems to me that there are different types of vacua that you discussed in podcasts. The de Sitter vacuum from your podcast on the nature of time, the vacuum at a black hole horizon, which gives rise to Hawking radiation, and the vacuum that gives rise to the cosmological inflation and the Big Bang. Can you please explain their characteristics and differences, if any? Yeah, that's a completely fair question. We use, as very often in science or in physics in particular, the same word to mean different things. The overall definition of vacuum to a physicist is, given some theory, what is the lowest energy state of that theory? So in ordinary theories, classical theories, empty space is the lowest energy theory and that lowest energy state, and that matches on to our intuitive idea of what the vacuum is supposed to be, empty space. Once you have quantum field theory, it's a little bit trickier. So once you have both quantum field theory especially and also gravity, so that you have space-time curvature, then it can be trickier. So we talk about not only the vacuum locally, that is to say, here I am in some finite region of space and time, and I look around and there's nothing there. And I can describe what is going on. There's always something going on in quantum field theory in the sense that there is some state that describes the state of the quantum fields around me, but it's the minimum energy state as seen by me locally. I call that the vacuum. But then we also have this situation where there is a global situation. There's a black hole or cosmology or whatever, and we can say overall, what is the lowest energy state? And usually, I'm tempted to say always, but usually those look the same in the limit of when you go, let me say it this way. Usually when I have some global vacuum state, that is to say the lowest energy state with a non-zero cosmological constant, so de Sitter space, or with a black hole nearby, right? Then if I just choose to look only at a very, very small region of space and time, it will just look like empty space to me, okay? This is one of the lessons of the paper that I finally did just publish with Chris Chalou, a graduate student, where we look at Hawking radiation and what it looks like to different kind of observers. The point is, long story short, but you need to operationalize that question. What do you actually do when you want to say, I'm detecting Hawking radiation? What kind of detector do you have? How long do you turn it on for? And all these questions. Quantum field theory is tricky. If you try to operationalize what you mean by the vacuum by saying, okay, I have a detector and I turn it on and off, the detector needs to be coupled, interacting with the quantum fields that you're trying to measure, and therefore turning it on and off tends to create particles. And even though you think you're in the vacuum, you're still detecting particles. That's one way of thinking about various effects in quantum field theory. Anyway, the point is that you can have different global vacuum states depending on the geometry of space-time, but locally they should look all more or less the same. The differences become subtle, like if let's put it this way. If our universe continues to expand and has a positive cosmological constant and lasts that way forever, we will enter the de Sitter vacuum state, and that has a non-zero temperature. So we say that Minkowski space, that is to say space-time without a cosmological constant, it has its vacuum state, and its temperature is zero. If you have a thermometer there and just let it equilibrate with the vacuum, it will say 0 degrees. Whereas in de Sitter space, there's a non-zero temperature. The thermometer you put there comes to equilibrium at a non-zero temperature. But that temperature is so extraordinarily incredibly low, the wavelength of a typical photon that is observed, that it is being measured, is as big as the universe. So if you're confined to a tiny little region of space, you're never going to detect those photons. To you, it's going to look like empty space. So there is some commonality in all these different notions of vacuum state. George Kandelopoulos says, priority question. In everyday life, we think of matter as physical stuff, Stuff like objects we can touch, and information as things like data or knowledge. But in theoretical physics, these ideas seem to be deeply connected, especially in ideas like black holes and the holographic principle. Can you explain how matter and information are linked in these contexts? I think it's a little bit casual, to be honest. I don't think there's a hard and fast set of rules there. Physicists are just as prone to speaking casually as anyone else, especially when they hope and think that the people around them will get what they are trying to say. But I do think that part of it is that as we dig more and more deeply into quantum mechanics and quantum gravity and emergent space-time and things like that, the fundamental stuff out of which the universe is made is a little bit less tangible than you might have thought. In Newtonian, when Newton wrote the Principia, if you said, what is the universe made of? He would have said, well, some particles, right? He even thought light was particles, corpuscles, but he was mostly thinking of, the earth is a particle, or at least is made of particles. He didn't know about atoms, but, he could imagine it was made of matter and things like that. And all that stuff existed in space, and it's all things you can see and touch. Whereas, if like me, you're trying to show how gravity can emerge from quantum information, well, you can very well ask quantum information about what, but the answer is some abstract d-dimensional factor of Hilbert space. What help is that? It doesn't seem as material as a particle moving through space. It is, by the way, just as material. It's just we're learning better what material means. And that's why at a philosophical level, what used to be called materialism as a philosophy of nature is these days much more likely to be labeled physicalism as a philosophy of nature, because it's a little bit misleading to refer to the ultimate stuff of reality as matter. Right? It's more abstract than that. Not that it's any, fundamentally less existent or anything like that, but we're not as familiar with it from our everyday lives. And what matters to us about it is the information that it contains. So physicists tend to talk that way just to go along with what their theories are telling them. Stevie CPW says, do you invest in the stock market? And if yes, what is your investing strategy or philosophy? Close to no. I probably should. I don't have enough money to be a major player in the stock market. Let's put it that way. I do have some retirement savings from working for many years at universities, and mostly I put those into index funds. That is to say, just follow the S&P 500 or whatever. I've had plenty of smart people tell me that is the best investing strategy, at least unless you are the owner of, some high-speed trading firm or something like that. So no, I do not have anything interesting to say about my investing strategy or philosophy. Sorry. T says, what do we mean when we refer to something occurring, say, 1 second after the Big Bang? I really struggle to understand the idea of measuring 1 second in that context, especially given the extreme and novel conditions of the universe at that time. There was no cesium, or for that matter, no atoms even born, much less having the opportunity to decay yet. Right. So, in some sense, this question is related to the one about measuring the expansion or acceleration of the universe. It is true that no one had a wristwatch available 1 second after the Big Bang, or any atomic version of a wristwatch. But time was passing and things were happening according to what we call the laws of physics. So the laws of physics tell us how quickly things happen as a function of time. And the way that we do it is we go back and forth. We build a model. So we have Einstein's general theory of relativity. We have some conjecture as to what the matter sources were and the energy sources were at those times. So we talk about what happened as a function of time. That equation we referred to earlier, the Friedmann equation of general relativity, is literally an equation for the scale factor as a function of time. So it is true that time is measured by clocks, but that's not all time is. Time exists as a parameter in our best physical descriptions of the world. And in that role, it absolutely has true meaning even 1 second after the Big Bang. Which brings us to our last question here from William Kittelstad, asking a priority question. What does science, math, economic theory, Warren Buffett, Bill Gates, and Marie Antoinette say when the wealth separation curve goes 100% vertical, which is fast approaching? wealth separation is proceeding at a mathematically unsustainable pace. The increasing concentration among a handful of uber oligarchs has created a class of relatively nimble humans and core with financial wherewithal to have agency rivaling, if not surpassing, that of nation states in the AI superintelligence realm. This presents a real threat to world order and civilization as we know it. So I know that's your priority question, but there weren't any question marks in there, but that's okay. I can talk about it. I do think it's a worry. I honestly do. I don't think most people listening will be surprised to hear that is my personal opinion. I don't know the exact numbers here because I'm not following it that carefully, but something like 20 years ago, the richest people in the world had less than $10 billion. And now there are several people who have hundreds of billions of dollars just a few decades later. Why in the world should that be the case? One can make a case that it should be the case, either a consequentialist case or a moral case. You could say letting certain people get all that money is part of incentivizing them to be innovative and create new things and ... You've heard the story before. Or you can have a more libertarian moral case that just says they have a right to earn money and you don't have a right to take it, and they've been very good at earning money. To me, neither one of these is very convincing. I'm a big believer, like I've said it many times, I have no problem with rich people or with being rich. I wish everyone were a rich person. That would be my ideal world. I just think that when there is inequality, we should tax them. We used to tax them much more effectively. In the 1950s, the top marginal tax rate was 90% for income tax in the United States. And now it's in the 30s or something like that. I'm not exactly sure. And not to mention all sorts of other things like inheritance taxes and capital gains taxes and so forth, generally lower than they have historically been. I think we could do a lot of good with, I think, two things. I think we could do a lot of good with the revenue that might be generated by a fair tax system. And number two, and this is something that has only become super noticeable relatively recently, we're putting too much power in the hands of a small number of people. I mean, I don't know if William knew this when he asked the question. I forget exactly when the deadline was, but we are seeing a small number of super rich people basically take over the U.S. government right now, up to and including getting information about Social Security numbers and payment histories for everyone the government deals with, which is basically every person in the country. That's bad. And it's all done in ways that are completely illegal. And a strict reading of what you're supposed to do. It's not even real government agencies that are doing this. And we have a system that is letting it happen, and it kind of causes one to shake one's head. And the real question is, how do we get people who voted for this to realize the terrible damage that is being done by it? You know, it doesn't do that much good to shake your fist in impotent outrage. We have to gather people together and get them on the right side of thinking about these things. We can't just say that they're idiots. We have to talk to them, understand why they would have done this. Is it because they didn't know what they were voting for, despite the fact that it was very clearly said that this was what was going to happen? Or did they actually want it? And if they did want it, what are the reasons why they would want this terrible thing? And I don't know the answer to those questions. I don't know the answer to those questions. I think it's absolutely worth thinking about. So we have built a system, short answer, in which those things are allowed to happen. I think that they're bad. I think that all the good things about capitalism, et cetera, can happen without people having nearly that much wealth and power as they do. And I say this as someone who doesn't believe, everyone should have exactly the same amount of wealth or power. I remember John Rawls, the philosopher who wrote The Theory of Justice, and he has this economic political system that he proposed that by most lights is incredibly redistributive, okay? He has what is called the difference principle, where he says in a well-functioning society, the amount of economic inequality should only be tolerated insofar as it benefits or advantages the least well off. Okay, so in other words, you're not allowed to invent a system where the worst off people become a little worse off, even if better off people become better off. That was his idea. So this is like super duper egalitarian, right? And there was an attempt at refuting this by Rawls's Harvard colleague Robert Nozick, called the Wilt Chamberlain example. And the Wilt Chamberlain example, this is like the early 70s when this discussion was going on. So Nozick says, and it's interesting he chose Wilt Chamberlain because they were both in Boston. I don't know why they chose the enemy of the Celtics. But anyway, the Wilt Chamberlain example says, look, Wilt Chamberlain is better at playing basketball than you or I are. People are entertained by watching him play basketball. They would like to give money to Wilt Chamberlain in order to play basketball so they can see him play, and this brings them pleasure. And as a result of this, Wilt Chamberlain has more money than anybody else, and everyone else has a little bit less money. Isn't this incompatible with the difference principle? So number one, this is like a bizarre example to use, right? He's not choosing a captain of industry here. He's choosing a basketball player. But number two, I actually talked to John Rawls about this. And I said, what is your take on this? And he was just so exasperated. He's like, go let people watch basketball and let people get rich and then tax them. Give them income taxes and then, not 100% of what they earned, but some fraction of it and use that to do good things. This should not be hard. It should not be hard to do better than we're doing right now. Apparently, it is hard. I don't know what to do about it, but we got to keep trying to do things about it. I guess that's as good a place to conclude as any. Thanks, as always, for listening, for supporting the Mindscape podcast. Always appreciate the support I get. Talk to you next time. Bye-bye.